Yeah. Ah, no, this one doesn't talk. It doesn't. This one doesn't. Oh, it does. It works. It works.
doesn't work, just speak loud.
Okay, very good. Okay, so
Okay. Okay. Let's start the second day of the winter school. Sorry for the little delay due to the technical problem. So the first lecture of the second day is again given by Professor Demgard. He's going to continue the lecture from yesterday. Let's welcome him.
good. Good morning, students. Beautiful morning in Beijing. Sunshine outside, so much light that you can maybe hardly see the slides. I didn't quite finish my lecture yesterday. I'll just quickly round up what we were talking about. I went a little bit fast. I was introducing an exponential representation of the S matrix, which is a very unusual representation that you cannot find anywhere else, but which is actually appropriate if you want to take the classical limit of a quantum field theory. And here we're talking about taking the classical limit of gravity, quantized gravity, quantum gravity. And now let's not start that discussion. Does it exist? I already told you yesterday that it does as an effective field theory, and that's good enough. If you want to hear more details about that, I can explain privately. So we're calculating the S matrix of quantized gravity, and we're going to take the classical limit. We put for our S matrix, we put the exponential representation, and then we're using what is called the K-Mach formalism, which very beautifully describes how you get a change in an observable from t equal to minus infinity to t equal to plus infinity. And you should think of that like the scattering of two black holes. That's the way to visualize it. You have two black holes coming in from far infinity, and they scatter against each other and move away to infinity again, or against flat space. And this is the process we're looking at. Now, suppose you want to calculate what is that scattering angle. One way to calculate the scattering angle is to instead look at the change in momentum of one of the objects. So you look at the incoming momentum was like this, it comes out bent. There you have the scattering angle. It's a question of geometry, and I'll just go through how that comes out and how that combines with the exponential representation. But in general, for an arbitrary operator, not just the momentum operator, any operator, it can be written as a difference of these expectation values. This is what is called the in-in formalism. In other words, you're not doing a scattering process like in-out from an in to an out state. You're actually measuring a quantity initially at t to minus infinity, and you're then seeing how does it change as you go to t to plus infinity. So here you have the operator, the expectation value operator at t to minus infinity. That's the starting point. And you want to see what does it end up becoming after having evolved from t to minus infinity to t to plus infinity. That's the time evolution operator, and you may recall that the S matrix is precisely the time evolution operator in the interaction section, say. And therefore, with this in state as time evolves goes to S in, and the in state, the bra, goes to S dagger acting on the other side like this. So this is just an identity. That is the difference in the expectation value of an operator from t to minus infinity to t to plus infinity. Let's move on and see what it becomes if we insert the exponential representation of the S matrix. It has this beautiful nested commutator form, which is very convenient for analytical calculations, actually. And like I said, let's look at just one operator. This is a general formula. Let's look at the operator that's momentum of the first particle, the first black hole. We see how it scatters. Let's calculate that. First of all, we should just know from geometry, like I said, if you know the change in momentum by simple geometry, you can calculate what is the scattering angle. The scattering angle we call chi, and there's a simple geometry here that says that sine of chi multiplied by the normalized impact parameter, and there's also an extra contribution, which is the longitudinal part of the momentum, it has a cosine, that is precisely giving that quantity delta p. That's without knowing anything about quantum field theory, quantum gravity, or anything. It's just geometry. Now, if we put our exponential representation into that set of nested operators and work a little bit hard, we find the following relation. We find that delta p can also be written in this form, where n is the thing that went into the exponent of the exponential representation of the S matrix. So n here is like the log of the S matrix. This is just what we get from quantum field theory. Now, then we compare these two expressions, and we read off that indeed chi, as we had hoped, would be is simply the derivative of this n that ended up in the exponent of the S matrix. And we see as a cross check, we get the same there with a minus sign that you don't worry about because cosine is an even function. And actually, deep down, just to tell you how it goes, we had an exponential representation of the S matrix. It's really a glorified use of the Euler formula between exponents and trigonometric functions. So that's a beautiful formula that we can use. It gives the change in momentum for scattering of two black holes to any order in gravitational perturbation theory. But it, as written like this, it has one, I wouldn't call it defect, but it is built in that way of presenting it, that actually we're calculating only the conservative part. What does it mean we're calculating the conservative part? When we have the two black holes, they scatter. If they don't emit radiation, then this formula is 100% correct. But if during the process they emit radiation, then this formula has to be modified. It's not surprising because that's the back reaction of the field on the black holes themselves. It's remarkable, but space-time makes these black holes wobble a little bit because they emit radiation, and actually the scattering angle will change because of it. So the back reaction, of course, is important. It's the back reaction that does that the two black holes spiral towards each other rather than just keep orbiting around each other without losing energy. They lose energy and angular momentum, and that's why they merge. That's why we see these bursts of gravitational radiation in the LIGO detector. So that we have to calculate as well. We have to take that into account. Otherwise, we just get the stable orbits of general relativity. That's nice, but we want more than that. And actually, we can include dissipation, radiation, and there's a simple way to understand how the formalism does it for us, actually. So let's look again at the change in expectation value of an operator. It could be the momentum of one of the black holes. And we can write it like this. Actually, we can also then simplify it as a commutator, as you can see. Just a simple rewriting and using SS dagger as 1. And then we can use the usual trick. We insert a complete set of states. Let's insert a complete set of out states. And then I'm skipping a line here. Believe me, if this is a complex conjugate of the out S in expectation value, you can, instead of putting the star, you can just revert it. And then you see that this is actually the sum. It's just the insertion of a complete sum of states. So this is just multiplying this, and this is just giving 1. And similarly here, it's just giving 1. But if O, or rather, if out and in states are eigenvectors, eigenstates of the operators, we just take out here the expectation values, and you can factor out the whole expression as follows. You have like an in state, it hits the S matrix, goes to the out state, and we're averaging over the difference in the operators from out, from t equal to plus infinity minus t equal to minus infinity. And here we have a weird thing. We have the in, S, out, but complex conjugate. And you may remember that if you do the complex conjugation, it's like time running backwards. Think of the time evolution operator. It's e to the I, h. H is Hermitian. You take the complex conjugate, you change the sign of I. So actually what we're doing here is we're running, if you think of it in terms of principle of minimum action, we're running from t equal to minus infinity to t equal to plus infinity. We're averaging over our quantities, and then we're running backwards in time from t equal to plus infinity to t equal to minus infinity. That may sound really weird to you, and that's because you probably haven't heard about the closed time path of dissipative physics. If you have, you know about analytical mechanics, how you do the standard minimization of the action over in the space of paths. But if you have dissipation, that principle doesn't work. You have to minimize actually in a closed time path. It's also called the Keldysh-Schwinger type of time path, and where you actually go from t equal to minus infinity all the way to t equal to plus infinity and then back equal to t equal to minus infinity. That's the path you want to minimize because that allows for dissipation. So this is the completely expected formula. And the interesting thing is, what happens to the radiated gravitons? Because normally when we're calculating when we are calculating in this formalism, we have two black holes coming in and we have two black holes coming out. But you should think of the following: the two black holes come in, the two black holes come out. But in the intermediate state, you can have all kinds of gravitation as well. So you have all the gravitons emitted in the intermediate state. The intermediate state in this case, remember, I summed over this intermediate state and I call them out states. Think of them as at t equal to plus infinity. That's all the radiation that went out. And then the black hole is, so to speak, moving backwards in time again to its good old self. This sounds like a fantasy, but believe me, it's right and it works. So when we calculate the formula I showed you with the nested commutator, if we just take the conservative solution, the one that doesn't radiate any gravitational waves, is the one where we just saturate the N operator itself by just two particle states without and all the gravitons inside the N operator expectation value. But in the nested commutator, you can also have insert complete sets of states with gravitons running between from N to N, and that's where the radiation sits. So this insertion of that extra set of complete set of states that now also includes all graviton states and even coherent states of gravitons, if you could calculate that is what gives the dissipation. All right, just to finish that little story, this has been checked. We've calculated up to order g to the 4, which is the only the highest order in which the complete result has been given in perturbation theory. And it agrees with others who calculated before us using what's called the world line formalism, but this is the amplitude version of that calculation. All right, this is what I wanted to say about the just to round up yesterday's lecture. I'm now switching to the second lecture, and that's going to be challenging. Let me see, maybe I should do escape, and then we hope it's sitting there. Indeed it is. How do you click? I hear click is right, and then this one. Yeah. Wow. Good. Lecture number 2. So the first lecture was a little bit quick. It was only, what, 5 minutes? A bit more. Anyway, I'm now moving on to a different topic, which I think is fascinating, which is how well, because now we've seen in the previous lecture, I hope you believe me, we know how to do perturbative calculations in gravity using quantum field theory methods. And now the question is, how well is that the perturbative calculation going to be? Many people tend to say, oh, perturbation theory is just dull. It's something, you have a small thing and you have even smaller things. You will never get the full answer. There's fantastic non-perturbative things you're missing and so on. Actually, perturbation theory in gravity is almost giving us everything. I'll try to show you that. So here's my outline of this second lecture. Indeed, like I said, scattering amplitudes, we've shown how to use them efficiently to calculate in general relativity. But maybe we can do better. We have seen that the post-Minkowski two-body problem can be solved. I showed up to order g to the 4, which is 4th order in perturbation theory. It gives exactly the right answer. And the question we first would like to discuss is, to which degree is general relativity actually perturbative? So more ambitiously, after having answered that question, maybe we could try to aim for all order results. So we're not just trying to calculate up to 2, 3, 4 orders, but maybe we could sum the whole thing, at least in some regimes. Maybe there's some way to do perturbation theory in a very clever way that Einstein could never have envisioned by just looking at his complicated equations. And I remind you, again, like I said in my lecture yesterday, that most people, when they used the post-Minkowskian expansion, they had this belief that basically it should only be valid very, very far away. Maybe 10, 20 Schwarzschild radii in distance from when the black holes are like 10 to 20 Schwarzschild radii from each other, then it would seem safe to use perturbation theory because it's almost flat space. But as soon as you get closer to the horizons, of course, you get more and more curvature, and there will also be the horizon effect. So you might worry what happens if you use perturbation theory close to the merger. But I have a kind of optimistic message in that today, and it's, well, like I said, conventional wisdom is you should stay very far away from the Schwarzschild radius. But I have a kind of optimistic message, and basically I want to rethink a little bit with you what we actually know about this. Why are we so scared about using perturbation theory further in? Are we really just stepping on our own shoes? And just not moving forward because of this belief that we cannot do better in perturbation theory. Now, you may have heard when you took your quantum field theory course that perturbation theory actually diverges. Are you aware of that? I don't see many people nodding. Of course, that's a shocking statement after you have learned about the Feynman diagrams and calculations, how to do them, Born expansion, and so on. And now you're suddenly being told it diverges. It's also very slightly biased way to put it, because divergent can mean many things. Actually, the expansions in quantum field theory, they're generically what's called asymptotic. So asymptotic means that, yes, indeed, they do diverge. But if you have a very small expansion parameter here, the coupling constant, if it's very, very small, and in particular, you can, if you tune it smaller and smaller, you can get better and better convergence. It converges out to a certain stage, and then it starts diverging after that. If you don't like that, you choose a smaller coupling, and then it converges further out. But it's only asymptotic. You'll never be able to take the full series. It's not even what's called Borel summable in most cases. So it's just, it can only make sense up to a certain finite number of terms. That's the generic behavior in quantum field theory. And it comes from, we can easily understand how it comes. If you have a generic object, f some function of the coupling constant g, we expand it as a power series in this g. But it turns out in quantum field theory, generically, these coefficients, they go, first of all, they oscillate in sign, generically. And they have an absurd behavior as they actually increase with n factorial. Of course, there are factors in front that keep it down for a long time, but in the end, the n factorial will win. So this is the behavior for large n, and clearly this sum is not convergent with this kind of behavior. Not only is it wildly divergent, it's even oscillating back and forth between plus and minus infinity. So this is what is called an asymptotic series. But that's due to quantum effects. So this is all due to h bar. It's quantum mechanics that does this. So that belief of perturbation theory having that disease has somehow penetrated into the general relativity community as well. And there was some belief that actually maybe also in general relativity, you cannot even do calculations like this. It will only at most be an asymptotic expansion you're doing. So you should be careful. Actually, it's interesting to think about it a little bit. There's an argument by Freeman-Dyson for why it diverges without even knowing that it has that behavior. He conjectured it much earlier on. The argument is the following. Let me see if I have time to, I think I can do that Dyson argument quickly. So in QED, take electrodynamics. You're expanding not in E, you're expanding in E square. If the expansion is supposed to be convergent, there must be a convergence radius. Maybe it's infinity, that would be even better. But at least there must be some circle around the origin in which the series converges. So let's do this Gedanken experiment. Let's think if the series converges around the origin in E square, so the origin in coupling constant space. So think of E square in the complex plane. Now, if you change E square to minus E square, what does that mean? In QED, what it means is that instead of having, like charges repel, you'll have like charges attract. Or conversely, opposite charges will actually repel. And Freeman-Dyson was aware, it was in the early 60s, he was aware that you can create pairs out of the vacuum in QED. So if that was really the case, that if E plus and minus would actually repel, you would actually constantly just produce E plus E minus pairs, and they would just repel, they'll fly all over the place into the universe, clearly showing an instability of the vacuum in quantum electrodynamics. It will just explode into more and more particles, and it will fall apart. So he conjectured from that it should be impossible, that it cannot be that there is a finite radius of convergence in quantum electrodynamics. It's a good argument. And later, of course, it has been confirmed by actual calculations. But the thing is, this doesn't really apply to gravity. Gravity always attracts. So there's no such thing as an anti-gravity. There's no way to make G suddenly change sign. And therefore, that argument doesn't hold. And the truth is, we know very little about the convergence of perturbation theory in gravity. So that's an interesting problem to work on, I would say, to say something rigorous about it. But in the meantime, we can play around. And I would like to do that by giving an example. That some work I've done recently with Kang-Hoon Lee from ICTP in Korea, where we have calculated the Schwarzschild metric perturbatively to all orders. And just to illustrate how the perturbation theory is capable of doing that. So what we do is instead of using amplitudes, we're using amplitude methods. You will see them in a second. But we're going back to the equations of motion of Einstein, and we are putting in a source, T mu nu here, which is simply a point-like I said, an elementary particle. You put in a point-like massive source at one point, It's static. It just moves in the time direction. It has no spatial component. It's sitting still, and we want to calculate what is the metric. So remember that we normally expand the metric G mu nu as the Minkowski metric plus some fluctuation field. This is fine. This is what everybody does. The trouble with gravity is that you also need the inverse metric. So if you define your fluctuation field like whatever is left over from eta, when you take the inverse, you have to do 1 basically. 1 over eta plus h, which is 1 minus h plus h squared, etc., etc. It's a geometric series. So in the Einstein equations, when you introduce the inverse metric, you're also including a completely silly iteration of the inverse of this one because it's just a geometric series. So you're really just making life hard for yourself. If you write it in terms of just the inverse metric, it looks beautifully simple. It's the Einstein tensor on the left-hand side of this equation. But once you start introducing the perturbation theory and include the inverse metric, it blows up. You get an infinity number of terms. And we're going to work around that. So we're going to use a trick to get around that. That's one of our ways to calculate the Schwarzschild metric in perturbation theory, but there are nice tricks as well. So let's look at the Schwarzschild metric, and I look at it here now in harmonic gauge. As you know, you can choose coordinates, and the metric is not unique. The metric has no meaning in general relativity. It's something we can compute in, well, no meaning. It is something that is obviously parameterization dependent. It depends on the coordinates. We can choose coordinates. You're used to seeing Schwarzschild, the Schwarzschild metric in the standard Schwarzschild form that he himself introduced originally in 1916. But we can also go to what is called the harmonic gauge, which satisfies a specific condition on the coordinates. And the metric looks as follows: d squared, and there's some function n. In harmonic gauge, n turns out to be a ratio like this. And there's another function f, which turns out to have this form. And finally, there's an extra piece, which has the ij components. Believe me, this is just the standard Schwarzschild metric in harmonic gauge. And then we do something that's sometimes used in general relativity, but by a minority of people. Instead of defining the h, like I just did there, instead of saying, this is of course the metric, and we say here's the Minkowski metric, and whatever is left over we call h. We instead define the fluctuations in the following form. We use what is called Gothic variables, so Gothic metric. And it's defined as follows: just square root of minus the determinant of g and g mu nu inverse. So the indices are upstairs. And we define as, say, well, this is going to be foremost just Minkowski, so it's eta, and whatever is left we call h mu nu. So it's not the same h as before. And we put also a minus sign because, yeah, that's. No, this is why do you call it unimodular? Who cares about the name anyway? No, it's not like the Einstein. Yeah, you're thinking of the Einstein choice. No, it's not that. Actually, this is the Landau. I know what you're referring to. Einstein liked that choice of coordinates. No, this is the Landau-Lifshitz. It's also called the Landau-Lifshitz choice of coordinates. It's the one you find in the textbook of Landau-Lifshitz, which I think actually is the first place it was introduced in the 1930s. So yeah, actually, thanks for the question, because it's good to remind ourselves, why is this allowed? We just defined before that we said the fluctuation field was, we took the metric, said it was equal to eta, and then whatever was left we call the fluctuation field. Now we say, well, it's this object, and whatever is left we call the fluctuation field. But that's the beauty of it all. We are just, we're in the laboratory, we have our chemicals, and we can mix them, and we can get blue liquids and yellow liquids, and we can stir around. We're in the lab of general relativity, where you can choose the formalism we find most convenient and what we like most. So we are now playing around with a different parameterization of what is a fluctuation in general relativity. It's different from the one we gave before. It's the Landau-Lifshitz definition of the fluctuation field in general relativity. So now just plugging in what the metric looks like in those coordinates, here it is. And the interesting thing is that so first of all, hij truncates. So there's only one order. It only goes up to order g squared. That's kind of convenient. All other high order terms are 0. And h00 has this somewhat ugly looking form there. But if we do a long series around 1, we can make it look much nicer. It's actually a peculiar factor of 8. Don't ask me what the deep meaning of 8 is, but it turns out to be 8 and then 1 minus gm over r to the minus 2. And then there's a minus 8, which basically cancels this, so it starts out as 0. And then there are two terms like this. And if you expand, actually what this H00 is, it is the first term has 4 gm over r, the second has 7 g squared over r squared, and the third term has this 8. And from then on, as you can see from here, the coefficient of the metric is actually 8 throughout. So that's just what H00 looks like with this choice of variables. That is the Schwarzschild metric expanded. You can say this is the exact Schwarzschild metric. If we expand in perturbation theory, it gives us this. The question is, can we get that also from the perturbation theory I've been talking about? By the way, note that the singularity is at half the Schwarzschild radius. We all know that the horizon, that this is just a coordinate. When you see a standard Schwarzschild metric coordinates, you see a singularity. That's a coordinate singularity. It's not a real singularity. The horizon has no real singularity, and here we see it explicitly. In this choice of variables, there's no there is a coordinate singularity, but it's at half the Schwarzschild radius. Okay, let's go back to the black hole. We have again the Einstein-Hilbert action. Here's the standard Einstein-Hilbert action, but we couple it to a source. The source we call J mu nu. This takes the place of T mu nu. And J mu nu, like I said, it's a static source, so it's a delta function in the spatial component. Let's write it in a kind of covariant way, a fake way, you can say, by introducing this time-like vector V mu. And then it's just this. So it's a point-like source that's just sitting still, and that's its tensor current. The delta function, it's kind of convenient actually to see that that's a Fourier transform. I'll get back to that. It's a Fourier transform of just 1. So let's now introduce a generating functional of this object, which has the explicit source. As you remember from your quantum field theory course, maybe if you do then the path integral over h mu nu, you define that to be the exponent of this w of j, a w of the source, which is a generating functional of connected Green's functions. Normally, when you're doing quantum field theory, you put in a source just like a trick. You just put in a source because it's good to take derivatives with sources, and then afterwards you put the sources to 0. Here we're putting in a source that's real. So we are not putting the black hole to 0 afterwards. We want to see what's the effect of having that black hole in space-time. Okay, and then what you call in textbooks, it's actually normally called the classical field. It's the vacuum expectation value of this object here. You can write that as the derivative of the generating functional, like this. And I will not go through it, but you can easily convince yourself of the following kind of master formula of Fourier transforms. You can write the h mu nu as some current j mu, which by just expanding the exponential, that's why you have the 1 over n factorial, and you integrate over the various momenta, can be written like this. And this is explicitly given here as this connected Green's function. Okay, now let's make use of this formalism. So let's start calculating in perturbation theory. So first we write down the equation of motion for the H field. We're taking the Einstein field equations, putting in the source J mu nu. That goes on the right-hand side of the Einstein equations. It goes into the T mu nu. And we're just looking at what is the lowest order the field equation. It turns out to be very simple. It's just the Laplacian acting on H is equal to, well, it's a factor of 2, and there's also a minus sign. Don't worry about that. It's basically equal to the current. Importantly, so with H, we raise them with the Minkowski metric. Yeah. It's notable here that actually to lowest order, we only have the initial current we put in itself. If we have to go to higher order in the equations of motion, you may know that already the left-hand side of the Einstein equations has sources, gravity sources itself because of the self-interaction. So at higher orders in perturbation theory, it'll look a little bit more complicated than this, but it's good to start at this point. Again, here's the delta function just written as a Fourier transform. And what we find, you can see, so what is the current that gives rise, what is the capital current that gives rise to this equation? Here you have an L square, it's the Laplacian, so its Fourier transform will be L square. So you can easily see that this is going to be 1 over L square. There are some factors, I think there are also some 4 pi's missing, but anyway, yeah, I think there's some 4 pi's missing up here. But anyway, you can easily convince yourself that the current that gives rise to this is precisely a 1 over L square. It's not so surprising. This is simply the graviton propagator, you can say. So leading order, you have a source, and you're measuring what is the H produced by that source. You can just link that source to the point you are by one propagator. Here it is. It's the propagator. Okay. Yeah, that's just from the Einstein equations. Sorry? Yes. So this is the leading order from the Einstein equations, when we're just rewriting in terms of currents, and I'll come back to why we're doing that. So solving that, actually what you get is that it's really the Fourier transform of this. You find that h mu nu is 4m over r v mu v nu. Let's check a look. What does it actually mean? Well, actually remember v mu and v nu, they're just time-like. It was -1 and then 0 in the spatial components. So we just multiply them out. We get +1 here. So we get h00 is 4m over r, and we find that 0i and hij, they're all 0. Let's check if we can do it right. So to leading order, we got 4 gm over r, perfect. And also, there should not be any hij because it starts at g square, and there's certainly also no h0i. So we got that on the nose. And then scroll back. There, right result. But that's leading order. It's too trivial. Let's move on. So plugging in the equation of motion for h mu nu to order g square is still doable. It's not too complicated. And what we find is the following expression. The new current at second order in perturbation theory, so it's order g square, is written by there's some factors here that they are directly inherited from the equations of motion for the h mu field. And then it is the product of two currents. Indeed, what is happening here is we're getting a recursion relation, because you see the new current at second order in the perturbation theory is given basically by a product, or you can call it a convolution, of two lower order currents. And now for the H00 components, and hence also the J00 components, it's not so surprising that we get J0 on the right-hand side. That was all we had. But we actually now also generate Jij currents. And you see, even though we started out with 0 components here, the equations of motion fill in the indices. So they give us the kernel, you can say, that should be put into that convolution. And indeed, the Jij we build up by recursion. We build it from J00. So even though we started with a static source, it will have Jij components also. And if you Fourier transform, which I do there, we find that taking this after doing the integral, which is not difficult because these are very simple integrals, H00 to that order becomes 7m squared over r squared, and Hij becomes just m squared over r squared. R to the 4 and times xij. I'm now going to scroll back again just to convince you that this is a good result. Here we go. This was precisely one. We found the factor 1. Sorry, here's a g square explicit. In the other notation, g was included in m, so to speak. Every time you have a capital M, you also have a g. So if it says m squared, it was really g squared, m squared. And also we got 7. That odd number that just comes out, it's the Schwarzschild number coefficient in these coordinates. And we got it from the calculation. So that's good news. We will go to order g square. Actually, we went ahead, also did g cubed. I'm not going to show you that because I want to remind you of the trouble with gravity. The trouble is that the equations of motion get worse and worse if we go up higher and higher order in perturbation theory. Partly and mainly, it's actually due to the fact we're taking the inverse metric, which becomes a geometric series in the actual metric. That just, it generates an infinity of terms, and you get more and more factors of g. Hence, more and more factors of h, more and more vertices, if you want to put it in that way. And let's see how we can get around that, because otherwise we will get tired. We can calculate to g cubed, next g to the 4, but we want to go all the way out to infinity. How are we going to do it to infinity? Well, there is a trick. So again, we need both the metric defined now in this way, this Landau-Lifshitz type notation, but we also need its inverse, the actual, you can call it Landau-Lifshitz metric. And this leads to this infinite series named h mu nu. I call that a non-fundamental nuisance. It's an annoyance. It's just annoying that we have to invert that metric and it generates an infinite series, because we know that it's summable. It's just a geometric series, but we're just putting it in order to do the perturbation theory. We're kind of wasting our time doing that because we want to actually sum it back again. So if we could avoid this expansion of the inverse, we could make the calculations much easier. So there is a trick to do that. It was not introduced by us. I forget who precisely did it first, but it's convenient actually to think of two independent metric, quote unquote. So you have the actual variables that you're working with. This is one we call Gothic, G. But let's introduce another one, just in the kind of auxiliary field we're using for calculations. And in the end, we know that it's just going to be simply related to G by this relation. It is just the inverse of the actual Gothic one. So if we do that at various stages of the calculation, we avoid this expansion of the inverse and generating this infinite series. Now it truncates. The equations of motion truncate at a finite order in G. Yes, indeed. So you have to do so, right. So similarly now we expand, is precisely what you're asking here. So we similarly expand also the new variables perturbatively. It has a funny h twiddle, but since you have this constraint, it's very easy to work out actually what is h twiddle in terms of h. So any fixed order, there's a simple relation between them, of course, and we have to impose this in the end. But now we do the following. We simply do the double recursion. So we do a recursion both in the actual h we're expanding in here, and we also do the recursion in this new field that's like an auxiliary field. And that will have its own peculiar, it's a good question. What kind of expansion will that have? It has its own peculiar perturbative expansion that doesn't look at all like the Schwarzschild metric. It's just a tool. It's just another field we're introducing, and it actually it makes the life easier when you are calculating. In the end, it goes away completely because we want only this. So, but at the cost of doing a double recursion. Remember, I showed you just the recursion. How you took a current from it's a current recursion. You take the current at a given order can be written as products of currents at lower orders, always adding up with the right factors of G. So perturbation theory works. But it's recursive. You calculate the new one by some integral over the previous ones. So you have done a lot of work when you go to the next order. You just have to do a little bit extra to combine the lower order terms. That's the current recursion. Now we have to do that twice. So we have to do current recursion both here and here. This is the price we pay, but it's a small price in terms, considering that we are then avoiding this infinity of terms. And what we can prove by induction actually is precisely this. So I will spare you the details, but we write down what the two expansions give. We assume it holds at order n, and we prove that that form also holds at order n plus 1. The order n, where we have to start, I can use this one and use this slide. Actually, yeah, the order n where we have to start is precisely this term. So we had to cube it to calculate up to this order cubic in G. That's the first time this coefficient 8 occurs. Remember, this is just a geometric series. So all other terms are just multiplied by 8 all the way. And actually, what we can prove by induction is precisely that if we assume that this coefficient is 8 at order n, it's also 8 at order n plus 1. So induction, of course, is a little bit also like recursion. And so this is the starting point of the recursion. And similarly, we can prove that all other terms starting from G cubed, it is 0. And then again, if it's 0 at order n, it will also be 0 at order n plus 1. So we actually get, from perturbation theory, the exact Schwarzschild metric. So I believe this is the first time ever that perturbation theory has been used to calculate in general relativity something to all orders. It is the most trivial example we can think of, well, roughly, the most trivial example we can think of an exact solution in general relativity. And we see that actually perturbation theory is capable of reproducing that. So you may not believe in gravitons, or gravitons don't exist, or quantum gravity doesn't exist, even though it exists as an effective field theory and so on. You may not believe all that, but here is certainly the proof in the pudding that it works. So this kind of perturbation theory is capable of reproducing an exact non-perturbative result. It's convergent, by the way, down to half the Schwarzschild radius. Remember that? It's not 2 GM over R, it's GM over R. Now, we should not be too excited about this fact that it's converting down to half the Schwarzschild radius, because, like I said, the horizon is a coordinate. I mean, the singularity of the horizon is a coordinate artifact. So we can find even coordinates, as you may know, like Kruskal coordinates, where there's no singularity all the way down to the origin. So this coordinate singularity is movable. Everybody knew, and still there was sort of a fear of the Schwarzschild radius. There was this fear that in perturbation theory, we should stay very, very far from the Schwarzschild radius. Otherwise, it would not be valid. There would be all kinds of effects that we would not get right. Well, in the simplest case, where we can really test it completely, it's not right. Perturbation theory works perfectly. Okay, that is the optimistic message of my second lecture. And indeed, what I would say is that it gives hope that perhaps this perturbation theory may work much better than we've been thinking. So I would say it gives stimulus to a program where you want to say, we don't want to just calculate sort of g to the 4, g to the 5. Maybe we can actually be ambitious and try to actually get regimes in which we can calculate to all orders in G. In this static case, we can. And you might imagine that there could be other regimes in which you can get all order results in G from perturbation theory. And presumably, I mean, there might be some non-perturbative effects that are missed in classical gravity, but it's hard to imagine what there are. And so at least it will give a huge contribution of the full results of general relativity. Okay, I think the way forward is that we have to use all the amplitude-based methods we've been going through. This calculation I just mentioned that I've recently done with Kang-Hoon Lee, uses amplitude tools, but it's not an amplitude calculation. We used amplitude language, quantum field theory language, where we were just calculating an expectation value, in this case, the expectation value of the metric itself. And the integrals we got were integrals that appear also in amplitude calculations, but there was no quantum mechanical amplitude as such. We're really calculating just straight from the Einstein equations, but using tools from quantum mechanical amplitude. So we now, it seems like we reached the stage where we liberated ourselves from this distinction between whether we are doing classical general relativity, we're doing quantum mechanical amplitudes, we're trying to take the classical limit and so on. It's actually all facets of the same calculation. They're really completely coherently linked together. And you can also wonder, how is it possible that quantum mechanical amplitudes with Feynman propagators and all the usual machinery of quantum field theory, how is that relevant for solving the Einstein equation? But then if you think a little bit further about it, how would you actually solve the Einstein equation? How did we solve them here in the case of the Schwarzschild metric? We used green function methods. So we used here a current language, which is a disguise of the green function. But when it comes to it, we're solving the Einstein field equations, which are second order differential equations. We solve them by using a green function. The green function translates straight into a propagator. There are details. There are things like, should you use the retarded propagator, the advanced propagator, the Feynman propagator, and all that. And these are technicalities that to leading order actually do not even play a role, but which one can sort out. So what we're seeing is that it's convenient to use classical field equations using the language of quantum field theory. Even though everything is classical, it's the green function method, really, that we're just reinventing in the light of quantum field theory. And we're using all what we know from quantum field theory amplitudes, including hard integrals in momentum space and so on, that people need to do calculations to calculate processes at the LHC. We're using them now to solve classical field equations in gravity. So actually, with Kang-Hoon Lee, I'm currently working on extending this program to the two-body case. So you could extend this, like, instead of having just one Schwarzschild black hole, you're calculating the metric. You can also think that you're having two Schwarzschild black holes, two sources, and you speed them up. You give them some momentum in the center of mass frame, they move towards each other, and first of all, you're calculating the metric of that combined pair. And then you're also seeing how does that metric affect the motion of the two black holes as you move? And we do that in perturbation theory. So it's importing that calculation we just showed could be done to all orders. We're now importing it into solving the two-body case using only the Einstein field equations and tools from quantum field theory. Yeah. Yeah. So we see that's the brilliant thing. Like you see that if you have the source, you automatically get the you get the metric for free, right? You're solving it from the source. So if you put in the sources, then you solve the equations, and then you get the metric. Are you saying which gauge choice we would use? Harmonic. Yeah, so we would like to have the standard, but it's not required. But it's a useful propagator. It has very nice properties, as you know. And again, the metric actually drops out because actually we're calculating only the what we call the geodesics. We're calculating the motion of the matter particles. But of course, the interactions are given with some exchange of gravitons. You may not like it, but gravitation. Something is being exchanged. And we're looking only at the motion of the two scattered particles. But H, of course, we have to calculate as an intermediate stage, and that is done in a certain gauge, here harmonic. Okay, I had one more line on my slide, but that one disappeared. You know what I actually said? I will say it in words. I had one more line here. I don't know, this computer ate it. I said...
Just go forward. And again forward.
Yes, thank you. Great subject for young students. Are there anybody in the room looking for challenging problems to solve? Or you just want easy problems? Anyway, I end there.
Okay, we thank Professor Damgar for the very interesting talk. Any questions? Yes?
So Professor, I was wondering whether this result is now based. Can you use harmonic base?
Yes.
So I test the base, so I test the alternative or for the
yeah. So it certainly depends on the gauge. I mean, the metric does depend. We call it gauge, but it's actually the coordinate choice as well. So it's some condition on the coordinates. And like I said to Laurent, we use harmonic gauge. We use that also in the calculation of Schwarzschild metric. So we get the Schwarzschild metric in harmonic gauge. And we must be aware that it's not a meaningful quantity. The Schwarzschild metric by itself is coordinate dependent. It is dependent on that choice. So it is a gauge dependent quantity we're calculating. So you can say this is a kind of proof of concept that we know how to calculate something to all orders in perturbation theory, but it's not a physical quantity. A physical quantity would be something like actually like the scattering angle of two black holes that go around each other. And there we would also use harmonic gauge. Like I said to Laurent, it's just a convenient perturbative gauge. There's no doubt about it. It is the most convenient perturbative gauge. It has a nice projection operator in the numerator, 1 over L square, and then there's a nice projection operator on the top. In the end, actually, when we're calculating black hole dynamics, we don't care about metric which coordinates is calculated in, because that motion will not depend on the coordinates. When finally we're calculating the scattering angle, that's evaluated from minus infinity to plus infinity at flat space. It's a gauge independent quantity. So it's a coordinate independent quantity. It's something that can be measured by LIGO, or for instance, light bending around the sun as an example, a similar effect. So that's a gauge. We're only interested in the gauge independent observable.
Yeah, you have a question.
Thanks for the lecture. Exactly what are we perturbating here? Like in QED, you're perturbating through internal particles, something like this. Like
yes.
When you have like higher orders of G, what is actually perturbating?
It's a good question. So I didn't get to draw it. I should maybe have drawn a few Feynman diagrams to stimulate our thoughts. So the diagram, if you want to think about it in terms of Feynman diagrams, these include all triple vertices, quartic vertices, quintic vertices, and so on of gravitons. If you want to think in standard perturbation theory in terms of Feynman diagrams, and all the loops they generate, but such that there are no closed graviton loops. So all because gravity, like in Yang-Mills theory, will have also closed gauge boson loops. They're quantum mechanical, but everything that hooks on to one of the massive propagators has potentially a classical piece in it. And those diagrams we're including. So including all diagrams of general relativity with all the vertices, if you do it the old-fashioned way, with all the vertices and so on. In this last way of writing it, we didn't have all these vertices. We only had actually triple vertices. So the equations were only cubic. Excuse me? Yes, gravitons, yes. Gravitons and self-interacting gravitons. That's what builds up general relativity. Yeah, the Landau-Lifshitz one. Translate, what do you mean?
Trace this.
No. It's all the remaining. No, but this is standard. And it's also not it's not even the fluctuation of the metric. It's a fluctuation of the Landau-Lifshitz upper index object which is a tensor density. It's not the metric. Yeah, so it's just a convenient. Sorry. No, that's the whole point. That we're calculating only the gauge invariant observable. So we're not calculating. So here we calculate the metric, which is not gauge invariant, but we're calculating something that's gauge invariant, which would be something like measured from infinity to infinity, like radiation at infinity, angular momentum at infinity, the scattering angle of the two objects at infinity. These are all gauge invariant. They don't care about whether you use H upper index or lower index, density, not in, that's just a choice of variables in the calculation. It's a choice of gauge. In the end, we want to calculate something gauge independent, and as standard, as you also do in standard quantum field theory, you choose a gauge, you calculate something as gauge invariant. You don't care about that there are other gauges out there because you're calculating something that's guaranteed to be gauge invariant, and then that's fine.
Any more? Yeah.
Normally, when you consider perturbations, the Herschel form is simple, where the volume is
yeah.
How do you compare to
The metric, how does it compare to the Schwarzschild? The factorized form. What you? I don't know what you mean by the Herschel form. This is the one this is the one that truncates. The one that truncates. The one I'm asking is what do you mean Herschel? You mean it's also called the Finkelstein maybe? The metric that truncates at finite order? Yes, that's an example of another choice of metric that does not have a coordinate singularity. So in the harmonic gauge, we still have a coordinate singularity. It's just half the Schwarzschild radius. It's meaningless. It's an unphysical singularity. But it means that our calculation cannot cross it. Sorry?
On one hand, you said it's meaningless. On the other hand, you are happy.
Yes, because people were so scared. They were so scared that this Schwarzschild, the horizon is something you should. Well, we're all scared about entering the horizon, right? But people are so scared of doing perturbation theory where you're close to the horizon because they feel that something should break down. I'm just saying, there are indications here you should not be scared because this calculation goes all the way into half the Schwarzschild radius. Okay, I don't want to extrapolate from that to say that also the scattering situation, you should have them you could actually have the two black holes overlapping and then still scatter. I'm not saying that at all. I'm just saying it gives us some comfort that actually we can calculate all the way. First of all, we can sum it, and it's convergent to half the Schwarzschild radius. So it gives us some feeling that maybe we can be more optimistic about the convergence of that series.
Maybe last question.
Okay, I wonder if this method can be used to calculate other consequences, for example, with field gravitational wave factor also.
So here we're trying to do the first step in calculating the signal of gravitational waves. We're calculating what are the orbits of the two black holes that will emit the gravitational waves. Once you have those, you put it into a machine and ask yourself, what kind of gravitational waves what is the gravitational wave signal of that motion? And this is what LIGO measures. So here we're providing the dynamics of the motion of the two black holes under the emission of gravitational radiation. We're not calculating the waveform. That would be a separate calculation. It can be done also using the same kind of formalism, but here we're calculating just the first step is to actually get the dynamics of the two black holes. How do they spiral into each other and finally merge? Was that an answer?
Yeah, that's answer. Also another question, what if there are no black holes, for example, in fluid?
No, you mean, suppose you just have two massive astrophysical objects that are not black holes, like neutron stars?
Oh no, I mean like something in fluid, not compact stars.
An astrophysical environment that actually has all kinds of matter? Is that what you're thinking?
Yeah.
Well, you think of a physical situation where general relativity has to be important, so it's presumably astrophysical, right?
Oh yeah, I see your point.
I mean, there would be some astrophysical fluid. That's a very complicated calculation, much harder than these point-like objects.
Oh.
Yeah.
Yeah, maybe you can postpone more discussions to later during the lunchtime. Let's thank Professor Demgar for the 2 wonderful talks. Thank you. So let's take a few minutes break, and we're going to set up the next lecture. Thank you much.
Sure.
开始好，没关系，我反正就是反正是相对性。
Okay, let's continue. And Professor Zhenxing Lu will continue his lecture on the scattering amplitudes of deep brains in the presence of T-duality. Let's welcome him.
Thanks. Yeah. Let me rephrase what the intention of this talk. Yeah. I guess yesterday probably I don't stress that, so probably get some of you confused. Yeah. The purpose here is I try to just the question how to implement the T-duality on the amplitude, the interaction amplitude between two deep brains. Here I just pick a specific system which consists of the dp brane and the dp plus 2 brane. Okay, thank you. Yeah. And these two place the parallel at a separation y along the transfer direction to both of the branes. So yesterday, I think I did probably afraid of not finishing, so I rushed it somehow. So I hope I recapped something so you know what actually I'm doing here. Yeah. Yeah. Yesterday, for the purpose, I tried to apply the T-duality to the amplitude. I computed the amplitude between a dp brane and a dp minus 2 brane, which one direction compactified along the brane direction. We call it longitudinal direction. So this is the amplitude I got after quite a bit the detailed computation. So here you see we have the infinity sum here. Well, the W just the one number runs from minus infinity to plus infinity. Yesterday I said if I take the arc to infinity, this should boil down back to the amplitude between these two brane without compactification. So how to do that? I think yesterday I wrote a little bit the rush. Yeah, here you see if you take the arc to infinity, so the only thing contributed is the one number has to be equal to 0. Otherwise, all the other non-vanishing one number will give the 0 contribution because of the exponential suppression here. So here you only take, so in that case you only take the w equal to 0. Then because of this is the volume of the because we compacted one dimension, so the infinity volume just the p minus 2, and because of the arc to infinity, so this just go back to the Vp minus 1. The spatial volume for the p minus 2 d brane. So as I said yesterday, if you take the arc to infinity, because also you take the one number go to 0, it's easy to understand because once it's open up this dimension, the brane can no longer winding on around that dimension. So the one number has to be vanished. So yeah, this just that's controlled by this exponential factor. So if you do that, you see this is back to the non-compacted case I gave you earlier. Here, yeah, just back to here. Yeah, everything is agreed perfectly. Yeah. So far I haven't done any T-duality yet. So I just give a starting point which can perform T-duality along the compact direction, which is just one of the direction along the brane direction. So. Okay, sorry. Yeah, this formula is just a starting point for us to perform the T-duality along this compact direction. Now, before I do that, I try to point out a few things which actually I stressed yesterday. So I said the oscillator contribution to this amplitude will not change it if you do the T duality. The reason for that is the only thing contributed for the oscillator, either bosonic or fermionic, to the amplitude is determined by this matrix, which is the product of these two. Actually, is a 10 by 10 matrix. Yeah, this just describes the p brane, this boundary state, and this describes the p-2 brane boundary state. You can see that it's pretty easy. Yeah. If you write out, this SP just equal to this time direction, this direction just a t of the positive one, and we have the minus one, which along the transverse direction, which is 9 minus p. So here you see, so anything is a positive one, that means along the brane direction. How many of them just count the brane you have, and those minus one just count how many the transverse directions transfer to this brane. So here is 9 minus p1. So you just see this. You know, in the deep brane bound state, you'll see how many. If you have how many of the positive unit tells you what's the brane you have. For example, for the p-1 brane here, of the p-2 brane here, you should have -1. So here should be p-2, and here should be 11 minus 2 p. So the multiplication of these two just gives the one I just write should be equal to just 1, 1, 1, 1. Here should be p-1 with one direction compactified, and we have -2 have minus 1, and the other all the rest also just +1. So this one should be 9 minus p. So as I said, the T duality boils down. But if we perform the T duality, the SP just goes to just should be if I do along the brane direction, one of the brane directions, this gives you good. Give this guy. So this should be, for example, I just choose one of them, becomes a -1, okay, for example, and the rest is still 1. Sorry, this should be 1. And the transverse direction, the original transverse direction is still -1. Yeah, the same thing I can do for this guy. This should give p-3. So you see, because I have the 1 is -1, that means this after T duality, this should become transverse direction. The direction transfers to the thing. So after T duality, so with the brane should be around the brane direction should reduce by 1, but the transverse will increase by 1. So if you do this, you will see because we will do this for both of this guy, so this will remain invariant. Either you along this direction. If you do the T duality on this direction, the story will be different. Yeah, this should be give you p+1. So this just because one of this guy will become positive. So you add up original the p1 plus 1 positive should give p+1. So in space I would write. So this because we do simultaneously either along the longitudinal direction to both of this brane, or you do both to the transverse direction. So the end result is this guy will the same thing as this guy. If you do along the transverse direction, if you do the longitudinal direction, if you do the transverse direction, this should give you this one, but this should also equal this guy. So that implies the oscillator contributed to the amplitude will be invariant under the T duality, either along the longitudinal direction or transverse direction. So that's basically the message I said yesterday. Here I just give a little bit of demonstration that probably make you a better understanding. The other issue I mentioned is the zero modes, the Riemann zero modes. The zero modes, the Fermionic zero modes contribute to the amplitude in the Riemann sector. So that only occurs when the two kind of brane has the same dimensionality. Otherwise, this Riemann sector will not contribute to the amplitude because each of the D brane carry different Riemann charge. They don't interact, right? So you don't have a Riemann interaction. Only for P equal to P1, then we do have because the two kind of brane has the same Riemann charge. So they have the contribution due to Riemann charge. So for this case, because when you do the Riemann, when we do the Riemann computation, we use this so-called GSO project operator, the boundary state. So this is symmetric between you set the eta when you define the boundary state eta, the +1 or -1. You're symmetric between the two. So you do the T duality as I demonstrated yesterday. The only thing you just this matrix element is for this one become to this one because we just we only shift this curve operator will becomes -1, and one of the direction if we do for longitudinal direction, this one also becomes 1. But this this minus sign is only give us a possible sign change over here because the charge conjugation also could be a sign. So we have the overall sign. So that's better if you boil down, just send this one to this guy, because if we have because for P equal to P prime, if you have a positive sign, we have the positive sign for both of them. If it's a negative sign, it also appears for both of them. So this kind of matrix element will remains invariant. The only is you don't have a sign issue. The only thing we just change from the eta to minus eta, because eta can be take value only +1 or -1, because this GSO projection is symmetric between plus and minus. So that implies if you use this the GSO project the boundary state, the whole system will remain invariant under the T duality. I don't know if I get you follow what I said. Because the T duality for each of individual, for this guy, for this guy, for example, T duality will change this plus to -1. And the -1 will put +1. So we could have the overall sign, but the matrix element will be remains invariant. The sign will cancel. So that if you use this GSO projector for this projected boundary state, so this T duality will remain the invariant for the zero mode part for the matrix element between the left and right. Yeah. So the bottom line is on the GSO projection, if P equal to P prime, the two has same dimensionality, then the matrix element would be invariant on T duality. So the only thing has a possible change is the bosonic zero mode, as I expressed yesterday. So given this understanding, so that's what we get the back. So, I couldn't. It's frozen. Oh, let me see. Okay, thanks. So that's for the case we discussed here, because the dp minus dp, because the Riemann sec will not have contribution because the two brane has a different Riemann charge. So the only part we have is contributed from the Navier-Strauss sector. Yeah, as I said, this part is contributing from the oscillator part. As I just described here, it will be remain invariant on the T duality. So given what I just described. So now we perform T-duality to this amplitude along the longitudinal direction. Longitudinal to both of the DP brane and the DP-2 brane. So that's should be pretty easy. Doing that, just doing this. If we send R, the T-duality tells us send the compact radius to the upper prime of the R, give the T-dual radius, and sending the winding number to the moment number. Then we just moved from this brane interaction to this one. So we denote it as here. So by doing this, yeah. So we just move back a little bit. You will see that, yeah. So we just send this R to upper prime of R, also to this R here. Then send the winding number to momentum to W to K. Then we end up, because I said this part will remain invariant on the T-duality. So we end up with the amplitude of this guy. So what this is, so this tells us the amplitude we get after T-duality is between a DP-1 brane and the DP-3 brane, with one direction compactified now along the transverse direction, right? So that implies this Y is no longer the original Y. Yeah, because the transverse direction for this brane, we should have 9 minus, the 9 minus P minus 1, it should be 10 minus P, right? But 10 minus P, keep in mind, we have one direction compactified. So non-compact direction is still 9 minus P, right? With one direction compactified, with the compactification radius is R. So this is the amplitude that we have. So to compare with the amplitude we have before, I just redefine the P minus 1 as P. So we can rewrite this formula just in terms of this form. We just relabeling because it's P for any P, right? So we just set P minus 1 as P. So we change everything here. So this is minus P minus 1 is P. So P minus 3 should be P minus 2. So here is P minus 3 should be P minus 1. And yeah, here is 9 minus P should be 8 minus P. But here, once we do that, you should keep in mind. So this guy is no longer 9 minus P, it's 8 minus P. This is why. So the direction transfers, the long compact direction transfer to the both of the brane. It's 8 minus P, no longer here. This Y is 9 minus P, but here is 8 minus P. Has 8 minus P direction.
Naive shifting you switch from chapter B to chapter A.
No, this one was just yeah, that's cool. Yeah, but this one should be both should be working to both. Yeah, because this P is for any P, right? Yeah. It could be from 2A to P to B. Yeah, but the things we don't know, the only thing we care about is we now have the interaction between the DP and the DP minus 2 with one transverse direction compactified. So this Y is constant the separation in the 8 minus P directions. Yeah. So, but you will see that. So now by T-duality, we obtain the interaction between DP and the DP minus 2 with one direction compactified along the transverse direction. Yeah, you could compute it directly from the compactified boundary state I presented earlier, because the only thing we worry about is zero mode, right? Let me give you. Earlier I give you both. So this one is okay. Yeah, this one is the boundary state for zero mode for the X field zero mode part. If we do the compactification along the longitudinal direction of the brane. But I also give you the zero modes for the bosonic X with one compactification along the transverse direction. So you could use this boundary state to do the same, perform the same procedure to compute the amplitude computation. You should end up with the one I just got using T-duality. Yeah, you should get this one. So, but I leave, if you are interested, you can do the computation yourself. But I wouldn't do that here again because of time limit. But I do give a check of this, why this one is correct. Is sort of the other way to check this, why I got the suppose I should convince you why this should be the correct one. So by doing that, what I'm trying to do, I'm trying to say, for this case, unlike in the amplitude I got for the compactification along the longitudinal direction, I take the R go to infinity. Here, if I want to go back, I need to take this R also go to infinity. So it's just to do the decompactification. But here the story will be different from the previous one. The previous one, you see, if I do the decompactification, because I take the R go to infinity, the only thing I need to take is W equal to 0, right? But here you see, because the R appears now in the denominator, so the story will be a little bit complicated. If you take R go to infinity, that means you have to take the momentum, you have to count all the momentum contribution. That means you have to do the sum to back to the formula you should expect. So how to do that? Yeah, because you take the R go to infinity, the sum can be written as an integral. So you just because I defined the z coordinate, which is given by this k is momentum. So that implies the I did something wrong here. Okay, this one should be it's right. Yeah, okay. I just remove this to the other side. Okay, then you can define the integral element dz just given by this because it's k differ by 1. Because I go to infinity, this infinitesimal small, right? Because this has to be small to you define the integral. So that implies the sum of the infinity sum can be written as an integral from minus infinity to plus infinity. Okay, if you do this, you'll find the infinity sum of this guy. You just go back to the we just take the infinity sum back to this inside the integral. So you just do the summation. Yeah, you will find I think this standard one. You end up with this guy. Okay, then you plug in this back to this formula. You do some manipulation. Yeah, you end up with this guy. So the coefficient is exactly the same thing as non-compactive case. So the only thing you interpret here is you see this y square is 8 minus p direction. But here the reason why I leave the x is along the relevant coordinates between the two, the dp minus 2 and dp. So this along the compacted direction. So this is arbitrary. So you add up, just end up with this should be the y I used in the non-compacted case is 9 minus p direction. Yeah, the transverse coordinate between non-compacted direction. So by doing this, I repeated exactly the formula I gave earlier for the non-compactify between a dp and the dp minus 2. So this give an indirect check. The formula I got is most likely is correct. It should be correct. Okay, yeah. So yeah.
Also, there's a difference in the dimensions, longitudinal dimensions of the two deep brains.
Yeah.
So that means by longitudinal or transverse.
No, actually, it's longitudinal to both of the brain. That means, for example, because I have the dp brain and dp minus 2 brain, so the common one transfer should be to this guy. So it should be 9 minus p direction. So this is y is 9 minus p direction. But
some longitudinal direction, dp brand might be transferred to dp minus 2 brand.
Yeah, indeed, because for example, for this guy, the two longitudinal direction should be transferred to this guy. But the thing I consider that because I want to preserve, I want to get always the dp, the difference between the guy always differ by the parity always differ by 2. If we do that, the story will be different. Then that kind of thing could be break more supersymmetry. Yeah. But this case, anyway, is break all the supersymmetry because we have interaction, non-vanishing interaction.
The TDI interaction always referring to.
Yeah, all refers to the common direction, either longitudinal or common direction, or, to the transverse direction. Yeah.
And not talking about that two directions.
Oh yeah. Because the two direction, one is longitudinal to this guy, one is transverse to this guy. Yeah. Yeah, that could be. Yeah. I have the that could be done too. Yeah. But I just get the simplest ones, it's easy to follow. Yeah. Okay. So by do this, just by this, I just demonstrate the formula we got here between dp minus 2 and dp with one transverse, one common transverse direct to both of the brane. Yeah, should be correct one. So with this two formula, you can do the TDR back and forth. If you want to do TDR on this guy, you back to this guy. If you want to do TDR on this guy, you back to this. Yeah, so for any compatibility radius, here just the I is just arbitrary. So with this, you can do you basically can do either of this. Yeah. So for both of this guy, this guy should be the same because I said we do the compatibility, do the TDRT. This guy will not change because those are contributing from the oscillator mode. Okay, given this, then I actually very beginning I try to do something a little bit different. Use a simplified version. I will demonstrate for this guy. You can do the TDRT actually without doing this kind of fancy computation here. You can do a simple version just like we do in the larger supergravity TDRT. Yeah, but there's a requirement. All I'm saying, if you want to get a non-compactified how the TDRT acting on the non-compactified the amplitude. Yeah, we can do something different. Yeah, a little bit simpler. Actually, very early I do this, but this only works. Let me try to emphasize that it only works that you can do on the TDRT on the transverse direction, not for the longitudinal direction. Yeah, very beginning I do the simpler one. That it works for this guy. For this the longitudinal TDRT. But for the transverse one, for the longitudinal one, it doesn't work. So it forced me back to do this. Yeah. Okay, let me describe why it works. Okay. So here, because if we for example, we can start from here, from between D0 and D2. If you do the TDRT, I'm describing in a moment. Well, from here I can get all the other dp and the dp minus 2 brane, the interaction amplitude. So this guy is non-compatible. The y is non-compatification. Yeah. For doing this, so here you see we just do, for example, we do the one TDR as one TDR at one time. So it's initially, so since it's a D2 and D0 brane, so the transfer direction to both of the brane is x3 squared plus x5 squared, x4 squared up to x9 squared. So I just divide this. I will going to do TDRT on an x3 direction. So I just write y bar square as the rest of them. So put it this way. So I want to do the TDRT on this direction. The first thing I need, because I want to do TDRT, so I need to compactify this guy. But how to compactify this kind of amplitude directly? So for that, I have to place this kind of system periodically along this direction, along the X3 direction, so that it give an effective compactification. That's what I'm trying to do here. For example, I put the D0 brane along the X3 direction, which is transferred to the D0 brane. I put it at origin, the X3 equals 0. So periodically, I mean, put the whole system periodically. I means I place the 0 brane along the X3 direction, along the transfer direction, just like given by this. So the m takes the integer as 0 plus minus 1, etc. So for the D2 brane, I'll place it this way. Because since these two guys are separated by X3, if nm equals 0, so that's supposed to be the case. Yeah. Yeah. Given this, that means the D0 brane is placed in the origin along the transfer direction. So the D2 brane is placed because of the original separation is given by this. So that implies I have to place D2 brane along this direction. So the difference between these two guys, because this mn, so I label this both of them take the plus minus integers. So I just label this to see the difference. So the difference is given by this. So the square of this guy should be given by this. So now that the interaction between D0 and D2 is periodic, because I place D0 periodically along the X3 direction, I also place the D2 brane periodically along the X3 direction. So for any of the N and M, the separation will be different. So you compute the interaction between the D0 and D2. You sum up for these all integers. That means actually we have the infinite copy of this interaction between D0 and D2. So since we know for each of this N and M, we can compute the interaction using this formula. So you just plug in here. So you see here, so the only sum is counted to this guy, because anything else is independent of the brane separation. Okay, if you do this, you plug in the y. I just I show you here, just the y square here. Then you because the n minus m is only appear here, so I can redefine set the k integer if equal to n minus m. Then one of the n should be redundant, right? So we change it from this sum to this sum. So this summation is just redundant because it is independent of the m. So this just give the infinity large number here. Basically, it tells the infinite copy of these interactions. So the k summation is given by this. So now we take the A. This A just the effective compactation radius, because we periodically okay, I should move back a little bit. Yeah, because I put the A here. This A is 2 pi A. We do the compactation along the X3 is the covering space. So each of the periodic distance is 2 pi A, which is just the A just radius of effectively just the compactification radius. So if we can do the sum, we have to take the A equal to 0. So we defined a z coordinate equal to x3 plus 2 pi ak. So dz just equal to this, because A is very small. So this thing, the procedure I described works only for the A goes to 0. Yeah. Otherwise, you have to do the sum here. So we want to do because we want to do the T duality. So we try to sum up this. So this you can do this, but do this summation to be an integral. Can be sorry, here is a typo. Yeah, to the integral, we have to set a go to a goes to 0. So that means dz is tiny. So that implies this guy should equal 1. So that means this sum can be converted to an integral. Yeah, if you do that, so this just the integration of this gives you this guy. So the amplitude for infinite copy of this interaction between d0 and d2, you end up with this form. So for an individual copy, because we have the infinite number copy of d0 and d2, so you have to divide this guy by the n infinity to end up with the final one here. So since for example the x3 is gone, nothing left, right? Because this one you integrate out, you only end up with this guy, nothing with the x3. So that implies when you do the compactification along the transverse direction, so you with one direction compactify, you take that the radius go to 0, you do the procedure here, you end up with this guy. So this y is y bar. That means the transverse direction is one dimension less than the previous one, right? So now we do T duality for this guy. The T duality implies we set the a, the compactification radius to a hat is the compactor radius, which is given by this. So since a wants to go to 0, so a hat should go to infinity. That's by a take x equal to 0. That means we do the T duality. We end up in the T dual version. We get an uncompactified interaction. But now it's not between d0 and d2. Should be between d1 and d3, because we do the T duality on the transverse direction. So basically we convert the direction original along the transverse direction to the longitudinal direction after T duality. So that's basically what. For d2, if you do the T duality on the transverse direction, it will become d3. For d0, you would be from d0 become t1. So this amplitude after T duality, you should be given by this. So that's what should we get here? Yeah, because a originally appears in the denominator. After T duality, you end up with this guy. So this guy we know the v1 times this 2 pi a hat, because this a hat is infinity, so the basically is just v2. If the a hat goes to infinity, that's what we did here to end up with this guy. So now the y bar is one dimension less compared to the one before we do the T duality. So this you'll see this precisely the formula we give at the very beginning. So if you don't believe that, we just move back. Yeah. The formula give you only for the long compact. Sorry. No. Yeah, this one. Yeah. If you take a p equal to 3, for example, here's v2, the p3 minus 1 over 2 just 1, just this fact. So the p equal to 3, yeah, it's 9 minus 3 is 6 over 2 is 3, the t3. So this guy just is vt. Yeah, this y should be transferred to d3 direction. Yeah. Sorry. Yeah, you see, it's exactly the same thing. So you can repeat this kind of process. You can from d0 to d2, then you can get D1, D3. From D1, D3, you can repeat the same process. You can get D2, D4, and D3, D5, and D, etc. What you want, yeah, you just repeat this process, yeah. So the reason for here, you see, it works because we can, the reason because when you do the compactification, we have to set before we do the T-duality, if you want to do the compactification, you have to set A equal to 0. Now, the reason for that, for example, because we do it in transpose, okay, otherwise, you see, let me give you some rationality for that. Yeah. You get this formula, you see. Yeah. If you don't set A equal to 0, then probably, yeah, this formula should be better, yeah. If you have a finite A, this formula will not be the, for example, I should divide by, if you want to get it right, you have this guy divided by n infinity. You end up with this formula. So this formula will not be same as if for p equal to 2, will not be the formula for this guy. Yeah, because we, let's see, the transpose, okay. Yeah, it will not be this, we will not look at this formula, for example, for d equal to p, if we set p equal to 2, yeah. Let me see, okay, yeah, if you, with one transpose direct compatible, it's not the same as this guy, this formula. So only if you set I go to 0 limits, because we do the compare, we set it, yeah, if not I not equal to 0, the formula I get here is certainly not the one I have here. I should divide this, yeah, the amplitude we should get is gamma divided by this guy. It's not look like this guy. Yeah. Only you set A equal to 0 limit, then this this formula will coincided with the one we just, the general formula I gave earlier, yeah, for this guy. Because as R equal to 0 limit, so the only thing you can take the K is K equal to 0. Otherwise, this blows up. This vanishes, right? Because now it's a denominator. It's R equal to 0. The only value you can take K has to be 0. Otherwise, the exponential separation has no contribution to that. So then, only for R equal to 0, you can take a K equal to 0. So this summation just simply drop. So you end up with just this simple formula if you take a P equal to 2. So only in those cases, if we do the summation, it will boil down to this formula. So you can, that implies if you want to, you can do the T-duality on the transverse direction only if you take the compacted radius go to 0. In that case, you can perform the T-duality. Otherwise, you have to back to the general formula I give here. For the general compactification, if you along the longitudinal one, you have to use this formula. For the transverse one, you have to use this formula to do the T-duality. I think that's more or less, I guess, yeah, my time. Yeah, basically that's what I tried to give in this lecture.
So the master case, if you were taking the limit of the radius R to 0, also the K should be
0 2. Otherwise, yeah, for example, otherwise you see, yeah, okay, let me back to here. Yeah, if we take R equal to 0, so this exponential separation, if K is non-zero, this guy is vanishing, right? So the only K equal to 0 has contributed to this amplitude. All the other non-vanishing K will not, the amplitude will be 0 because it's exponential. So So this way, when you take the r equal to 0, this boils down to the computation I just described. Yeah. Otherwise, but in general, for general radius, you should use this formula. The formula I just give you doesn't apply, doesn't work. It's not valid. Yeah. That the one I just give you, that's normally we do in supergravity when we do T duality. That's the one we use because with supergravity, the distance, the separation is very we don't see the source. Yeah, we just far away. You can do that kind of thing. You just count the zero mode contribution. Basically, it's k to 0. Yeah. We only the momentum. We don't have the momentum. We don't have momentum. In this case, we have only a momentum contribution. Around the compactification, because the only thing you have the momentum flowing around the circle. Yeah, for this case, it's just winding because the brane, because we have compared around the brane direction, the brane can widen on one of the direction can widen around the circle. Yeah, yeah. So yeah, all I'm trying to say here, for the transverse compactification, you can use the procedure simplified one I just described, but you have to take the compactification radius vanish. That can be applied to get the non-compactified amplitude. But from the longitudinal one, it doesn't work. Yeah, because you take r equal to 0, the W has to take infinity many of them. All the one is there. You cannot drop it. Yeah. So in general, you have to use this two form. For general radius r, if you're doing T duality, you have to use either of these formulas. It depends on which compactification you're taking.
Any other questions? Okay.
So can we still learn that from the convergence direction computation that in some sense like some recursion from you can calculate the D0, D2.
Then you can get you repeat this procedure. You got D1, D3, and D2, D4. Yeah, you just repeat this process. Yeah.
It's kind of like the recursion.
Yeah, it's sort of kind of yeah. You can yeah.
Okay. More questions? No questions at the moment. Let's thank Professor Lu for the 2 great talks. Okay. Let's take another few-minute break. We're going to prepare for the next lecture. 谢谢罗老师。 Okay. Let's continue. Okay, so the third lecture of this morning session is gonna be given by Professor Bai. It's gonna continue the discussion on the macroscopic dark matter. Let's welcome him.
谢谢。Okay, let's. Can you hear me? Right.
Yes, we can hear you.
Okay, thank you.
Yes.
So let's talk about second class of microscopic dark matter model, which is so-called long topological solid time. As you can see that here we're talking about long topological solid time. So there should be also topological solid time. In some sense, in the last lecture, the monopole object, for example, magnetic monopole, those objects, they are kind of like a topological solid time. And so here we will first discuss what's the meaning of a long topological solid time and why it's stable, what are their properties, and how do we perform some kind of calculation. So one is sometimes in the literature people call it a cubo. Another one which is made of bosonic degrees of freedom. For example, the constituency is a scalar field. Then there is another class of models. We can call it like a quark lattice or dark quark lattice, for example. So the constituency is fermion. So sometimes there is some property between those two a little bit different, but in general they have a little bit of common features. They all belong to this kind of non-topological solid. Okay, so let me start one class of non-topological solid time. I think earlier time, like what I was mentioned yesterday, like TDE, and he has studied this object till late 80s. Probably some later part of his research is about this kind of long topological solid. So what is this object? And also later on, it was kind of repeated by Coleman about this subject, and Coleman provided a better name, called it cubo. So what is this object? So this object is just read the words, is basically if you have some complex scalar field. So why it's complex scalar field? Because you want to kind of introduce some global U1 symmetry, and then you want to use that U1 symmetry as some kind of conserved quantum number, and then that kind of can justify the stability of this cubo-like object. So here, just like a toy example, which is also given in Coleman. For example, so you have a complex scalar field. You have phi absolute value square. You can think about that's just phi dagger phi or phi star phi, right? So you can look at other some kind of potential term will contain not just a phi square term, but also phi to the 4 and the phi to the 6. So that means this potential is a little bit contain non-renormalizable term. Just give you enough structure. So this potential, you have some minimal, which is when phi equals to 0. So that's a global minimal of this potential. And also you may have some metastable vacuum, for example, around 1. Take the global minimal and think about that would be the vacuum state. But it turns out that for some matter object, because of the finite density effect, the object could set at this kind of local vacuum state, for example. So how do we perform a calculation? So naively, we could just trying to let us go through the step by step. So you can think about that because there is U1 global symmetry, and you can think about the scalar field. This is a complex scalar field. You can parameterize that using some exponential IT omega. Omega will be the energy of this classical scalar field. And at times, some maybe we are doing this again spherical way. Then you have a phi as a function of a radius. Then you can calculate the charge. That one you can get the charge in terms of the omega. And the times the volume of whatever. If you think about this is some step function way, if this phi r object or cube. So like what I was saying, in a large Q, therefore the energy of the state will contain this part, partial d part, and you get this q squared over phi squared over v. But also in the meanwhile, you also have the potential energy part, which is the potential times volume. So now you say that both the one term, which is 1 over the volume, another term is linear in terms of the volume. So they are competing. Then you can minimize the energy respect to the volume. Then you get the extremal point for the volume. You substitute back. Then you can calculate the energy as a function of the field. Then you can see that it's proportional to Q, which is the charge, and times the square root of 2 times the potential divided by phi square. So that means that if we are talking about what we care, because there is a conserved U1 symmetry, we want to care about what is the lowest energy per charge. Then what we should minimize is not the potential, but instead we should minimize potential divided by phi square. So that means that we are not looking for vacuum state. We're looking for some like a finite density state. And so therefore the minimization, what we care is potential divided by phi square. Okay, so for the OE potential, we just saw this kind of non-reducible potential with this structure. We can calculate what is the potential divided by phi square. As you can imagine, when phi denominator, that's kind of make this a little bit larger. And it turns out that the minimal point for potential divided by phi square is around 1, in a sense, around I don't know, I guess, say the kind of a difference, right? So that means that in general, depends on the specific model, there may be some kind of non-trivial scalar conserved quantum number.
Recording in progress.
The preferred lowest energy per charge state is different from the ordinary vacuum state of the potential. And also this soliton state, then we can say that is a soliton state. And there is no topology to talk about, but we still have this kind of conserved quantum number to talk about whether how it's stable. And one can easily justify if this is the lowest energy per charge state, and then you can also say that that is also stable at a quantum level, even we just trying to solve the property of this state at a classical equation for motion, right? And to the charge and at times some intrinsic property of the potential, which is not super important. So here we just it's a little bit you need to have this kind of two local minimal features. You require a little bit long renormalizable potential. Now we can also move on to talk about a little bit renormalizable potential with not a single field but with two fields. So let me discuss another simple example. Another simple example is kind of well studied. So what are we talking about? So we first have this. Now we are talking about two scalar field. So one is phi, which is that contain that U1 phi global symmetry, that is scalar field, which you can think about that is the constituent of the cubo or long topological solid term. Another one, which is the existing particle in the standard model, which is the Higgs doublet. Okay, so we have the Higgs potential. So this is just a standard model part. So now we add this kind of very renormalizable interaction between the phi dagger phi and the h dagger phi h. Right. So simplest renormalizable interaction you can write down between Higgs doublet and U1 phi charged phi scalar particle. But in principle, there could be also phi dagger phi dagger phi, in a sense that there could be self-interaction of the phi particle term. Later on, we can turn on that interaction to discuss what's the difference. Temporarily, we can just talk about this simple, sometimes in the literature, people call it. There are lots of study and treat this phi as a ordinary like a particle dark matter candidate. And there are lots of study, I just give you a sense. Then there is a direct detection constraints, like we discussed last time. It's almost like the weakly interacting massive particle case. There is a lot of constraints about this particle, phi particle, for example. Here, just use MS in the like a few hundred GeV. There is a huge constraints from LZ and so on. Right? And, but it turns out that even in this very simple model, the dark matter may not be just in our ordinary vacuum, in a sense, electroweak is breaking vacuum. Though there is could be a chance that this model can already give us a non-trivial, non-topological soliton or cubo-like state. So how do we Lagrange? And we do the same thing like then we have and phi r. Time dependence and R dependence, then you can combine to write down the equation of and it's kind of a little bit straightforward. It's a little bit simpler system than the previous lecture when we talk about that paired black hole case. And so you have some double differential equation, two double equation for boundary conditions. You're trying to solve that. Okay. So after a little bit of solution, just give you example. Suppose here I'm trying to use example, which is lambda phi is the self interaction of the phi particle. We already at this moment set that to be 0. Later on, we will turn on the phi dagger phi interaction. Some coupling between phi and Higgs. And so here is showing, for example, we first look at a little bit large charge, like a Q500, for example, which is a solid line. And you can see that first the scalar field, the blue line, that is the little phi profile. You can see that it has a little bit larger field value around the center and some kind of tail behavior. And also interesting thing, if you look at the Higgs profile, when it's far away from this cubo long topological soliton, the Higgs wave is 246 GeV, is our ordinary electroweak symmetry breaking wave. But when it's inside of this kind of cubo state, the Higgs wave is close to 0. So that means that inside there is some kind of electroweak restoration, and very similar to the previous case when we talk about like a magnetic black hole in the large magnetic field, the electroweak symmetry can be restored. So here is a little bit different. If I switch back to give you a guidance, to give you a little bit idea, right? So look at this term. So this term is inside of the potential. If the phi field value is large, that kind of provides a little bit of positive mass for the Higgs doublet, right? So if that is over the original negative mass for the Higgs doublet, then you prefer Higgs wave to be 0 to be restored basically. So there is kind of an interesting interplay between the scalar phi field versus the Higgs wave showing up here basically. Another thing you can see that if the charge is not that large, for example, the charge is close to 20 or close to 21, roughly speaking, think about that both are comparable charge. And there are two types of solution. Let me say, one type, let's say this dashed line, and which is a little bit flat for the Higgs, and phi is a little bit shallow, is more extended. Another one, which is this dotted line, let's say Q21, it's Higgs is partially restored. There is a little bit density, large density for phi. That's also kind of interesting. That's also kind of a little bit generic. When we study those long topological soliton, sometimes for fixed charge Q, we may have two types of solution. Later on, I will show the energy per charge for those two types of solutions. So here I just want to emphasize that for large Q, for some object, very simple object, non-topological soliton, you maybe also anticipate inside that object, electroweak symmetry is restored, and we can call this electroweak symmetric dark matter ball, for example. Okay, so here it is a calculation for the mass minus Q times M phi. So this M phi is defined to be like a normal vacuum. We treat the phi particle, and so that will be coupling whatever lambda phi h times the electroweak wave, for example. So that will be ordinary phi particle. And so here is the Q ball or long topological soliton mass minus for the same Q. And if this is less than 0, so that means that you prefer for the same charge, you prefer to be in this kind of Q-ball state instead of a free particle. So instead of like a free Q phi particles, you prefer have them to group together to become this kind of non-topological soliton. So another interesting thing which I was emphasizing is a little bit generic. For fixed Q, you usually have two solutions. So the lower branch, so that is can give us a little bit stable object, which we can call it a Q-ball. There are also upper branch. The upper branch is the energy you does not prefer them to be bounded is positive, so it's not really binding together. So that is sometimes people call it a Q crowd state. Okay, and also there are some interesting. You can see that the stability for this Q-ball object, there is some ratio QS. So we can say, oh, that is like above that Q. Then you can have some object to be even stable at quantum level. And also there is a little bit of endpoint of those two branches. They overlap. That is the minimal charge for the existence of any this kind of long topological soliton solution. Below that, there is no classical solution available, for example. Even though I'm here, we are kind of discuss about both scalar constituents. It actually turns out that this behavior, this kind of general picture, showing up even when we talk about the fermion and Lagets type of quark Lagets or fermionic ball, for example. So they all have those characteristic mode-dependent QS and QC. So that's kind of become the general feature. So for this case, because we kind of ignore the self-interaction of the 5 constituents, in the large Q limit, one can get a simple relation. And it turns out that the charge is proportional to radius to the 4th part. The mass is proportional to Q 3/4 part, and also it's proportional to R cubic part. So it's very easy to derive this scaling behavior. So for this case, the mass does not necessarily proportional to charge because there is no self-interaction of those 5 particles. So in principle, we can turn on, we can introduce the self-interaction, which is the last term of those 5 particles, the constituents. So here, even we can proceed to do some kind of calculation, and in principle, we can just numerically solve the system. And but we can also just like intuitively trying to understand something, which is if you have the phi particle, right? So that will self-interacting. So that means that when the phi particle field dense profile become large, this term will cast energy. So in sense, the self-interaction of the phi particle, they want to kind of repel each other and they want to flatten out. Make like a little bit of approximation to convert this into self-interaction of the phi particle with a little bit of condition. Like I was mentioning, if the phi field is larger than the Higgs mass, then you prefer the Higgs wave to be 0. Otherwise, you maybe have some non-zero Higgs wave, for example, right? So maybe one can use step function ways to derive a little bit phi only effective potential. And then you maybe can use that to solve a single field double differential equation. And also you can using the Coleman's way and to think about this is like a one particle motion. And you think about this is a force. And this 2 over r phi prime is some kind of friction term. And you can use this language of a ball rolling or on top of a here. So you can think about there is some effective potential. There is a ball you put on at a certain location, you let it roll down. There is a friction, and it will slow down. And you want to have this ball at the large time and or to get into the original point. So which means the field value is small, as a way to think about how to solve the system, right? But in general, it's not necessary. One can just solve the classical equation of motion directly. So here just to show. And as you can see that this DMB2 versus DMB4, so this DMB4 contains that self-interaction of the constituents. So therefore, you have some kind of saturated omega. Omega is defined if you have some bare mass, you should correct that. Otherwise, it's the same kind of omega we previously talked about. Basically, there's some minimal omega. Below that, you don't have a solution, and above that, you can have a solution. And so here, just to give us some solution for the profile of this phi particle, and depends on for some two value of those potential parameter. You can see that once the omega at large, then you have some kind of certain size. But once omega gets smaller and smaller and closer to that previous critical omega, then you can have this profile gets extended, but more or less a flat step function like behavior. And this is also like what I was mentioning, like because the self-interaction will have a little bit of repulsive interaction among those constituents, so they kind of flatten out. For this case, in general, you have the Q charge, total charge proportion to the radius cubic. The mass is proportion to Q and a proportion to the radius cubic. The energy density is just related to the intrinsic scale in the problem. For this case, you say it's electroweak scale, for example, right? So by solving this object, long topological soliton, we kind of already see two interesting types of BEC state. So one is if the self-interaction is not important, we have a sum scaling, we already mentioned. The mass is a proportion to charge, 3 over 4 pi. And another case, if the self-interaction is important, we have a little bit simpler situation, which is the mass proportion to the charge, and that's it. Right? And in both cases, we could have if we couple to the Higgs doublet, then we have the electroweak restoration in the inner region of the this non-topological soliton. So in that sense, this is already very simple. It's just almost like it's just solving classical equation of motion, and can give us interesting non-topological soliton state. Okay, so that is the first model, which is QBall. Now let me talk about another, just a very analog to that, and which is we can call it a fermionic ball. We can call it a quark-lagged, but let us call it a quark-lagged. Because I feel like there is a little bit stronger motivation to discuss quark-lagged. Okay, so what is quark-lagged? So that is traced back to more than around like 50 years ago. There are some people, physicists, they were wondering that if you study some ordinary nucleus, if the ordinary nucleus can shrink, just read the second sentence, there may be possible elementary particles with mass number, atomic mass number, and with a smaller radius than ordinary nucleus. Basically, you say, oh, there's some object that carry the same baryon number as a certain ordinary nuclei, but the radius is much smaller. And so in some sense, that's an earlier time speculation about the quark nugget. So the quark nugget has obvious importance in the following sense, even though the title of the lecture is about dark matter. But in my opinion, if the quark nuggets can exist, that's more important, has another important consequence, because our periodic table only stop like a SN like a 238. So there is a upper bound for our existing periodic table. But if you have the quark nuggets, in principle, there could be another parallel periodic table. And so the largest atomic mass number or atomic number could be even larger than the ordinary periodic table. So in that sense, I thought is also kind of important, and which also kind of attracted my attention to study quark nuggets in recent years. Okay. So obviously everybody knows the ordinary nucleus, right? So it's made of proton and neutron, and there is a limited separation distance, roughly speak. And the proton and neutron, they are made of quarks, right? And we also know one more information about the proton neutron, which is their masses are mainly coming from QCD, and the QCD becomes strong interaction in the IR. And we also know that there is a potential some condensation for fermion, antifermion, or there may be some gluon condensation that maybe determine the QCD scale, right? So that's also how the proton gets their energy. So what is the quark nugget? So first, you can think about the ordinary nucleus, which is the left side. It's made of proton and neutron, and proton neutron, they contain 3 quarks, for example. And also they are in the confinement as well as chirosymmetry breaking vacuum. So in a sense, the those psi bar psi is not 0, G square is not 0. Okay, on the right side is the quark nuggets. So here I was literally counting the same number of quarks as the left side and put them together, put it as a smaller radius. But also another important thing is inside of the quark nuggets, there is no chirosymmetry breaking, there is no confinement, so they are kind of deconfinement. And so that means that they are in different vacuum states, right? So this is very similar to previously when we talked about the QBO, right? So except that's very simplified. So there has two minimal, right? And so here you could have not necessary, you need a necessary set in the global vacuum state, right? So because you have a finite density, you maybe can set in this different, even deconfined phase, right? And so what make the ordinary nucleus stable is because we have the pion, we have those nuclear interaction, right? So attract those nucleons together. So what make the quark nuggets stable is because this object is not setting at the ordinary chirosymmetry breaking vacuum and the confinement vacuum. So then there is a vacuum pressure because the vacuum, because we know that in the empty space, we know that the QCD prefers to have chirosymmetry breaking and confinement. So therefore, the ordinary vacuum state wants to occupy this region, because this region you say, oh, you're not in the global vacuum state, right? So therefore, there will be vacuum pressure to push. But in the meanwhile, you also have those quarks, right? Quarks are fermion. So fermion has a degenerate Fermi pressure, right? When we study neutron star and the white dwarf, for example. So there is over there is a balance between degenerate Fermi pressure versus gravitational pressure, right? So here in the quark lattices, degenerate Fermi pressure balance the vacuum pressure. Okay, so that means that we can introduce this vacuum pressure. And historically, sometimes people use the notation, this kind of a B. And also in the earlier time, people have so-called Beiger parameter and Beiger model, and that B will be like a Beiger parameter. Okay. So we can go through very, very simple calculation to orient it. So what is a calculation we can do? We can treat those fermions as a degenerate Fermi guys, those quarks, and we can ignore the interaction, even ignoring QCD interaction. So therefore, we have this is just a simple thermodynamic statistical dynamics estimation, right? So we have a Fermi momentum, we have lumbar density proportional to Fermi momentum, we have the total baryon number, or total number of quarks will be radius times lumbar density. So therefore, we can have the Fermi momentum to be 1 over r times the a 1 over 3 par. And then we can calculate the Fermi energy, and which will be the Fermi momentum to the fourth power times the volume. So that will be a 4 over 3, 1 over r. But in the meanwhile, we also know that this object is not sitting in the global vacuum state. So therefore, it should also cast vacuum energy. So that vacuum energy is just this vacuum pressure or vacuum energy, and that times the volume, which is r cubic. So now you have two terms. One is 1 over r, one is r cubic, and one prefer to have a smaller r, or has a bigger r, one is prefer to have small r. So then you minimize the total, then you will determine the equilibrium location of the r, so which is proportional to baryon number 1 over cubic, and in terms of the generic Beiger parameter, which is just QCD scale, 1 over the QCD scale. And also you substitute Beiger, you can calculate what is the energy per baryon. And so it's just proportional to the Beiger parameter 1 over 4 par. Then there's some kind of order 1 number, and also related to how many flavor you have. You have a 2 flavor, you have a 2 over NF, you have a 3 flavor, you can even lower it further by 2 over 3, 1 over 4 par. If I give you some number, if my Beiger parameter 1 over 4 par, which is the Beiger parameter is mass dimension to the fourth par. If I tell you, oh, that's 145 MeV, you will have the energy per baryon to be 917 MeV. Just to remind everybody, proton mass is 938 MeV. Iron, which is the most stable element, has the mass per baryon to be around 930 MeV. Okay, so therefore, if you have a little bit smaller Beiger parameter, then you could have this quark nugget to be even lower than iron. So therefore, you could have this to be even more stable than the most existing stable element. Okay. So that's why sometimes people speculated that this could be the ground state of the QCD. And that's what I mentioned earlier time is first pointed out by Bodemer. Later on was pointed out by Wheaton that, oh, you maybe can, instead of using up quark and a down quark, you also can add a strange quark. So therefore, you can have 2 over 3 to further reduce the energy per baryon. Okay, so Wheaton is trying to say that you could have a strange quark together with up quark and down quark nuggets in the 1984 paper. Okay, so now what this has anything to do with dark matter? So I tell you some possibility, some possible relation. So what is the relation? We know that there is one robust information about dark matter is the dark matter is a factor of 5 compared to ordinary matter in terms of the total energy in the global scale of the universe, right? So the question is why dark matter is has comparable energy density compared to ordinary matter, right? So you maybe say that's not a big deal, but however, for the ordinary matter, we have the long trivial story. We have the so-called baryon-antibaryon symmetry. We want to figure out why we have a 10 to minus 10 left over of a slightly little bit more baryon than antibaryon. And this is still on our to-do list to understand, right? What would be the underlying mechanism or underlying model behind this baryon-antibaryon symmetry. So far, we have a lot of models. We don't know how to explain yet. We don't have a robust proof, right? And there's some general Sakharov's conditions trying to explain this, right? So now if you think about, you take this into consideration, now you can think about the dark matter. Then you realize that it's more particular. Why the dark matter is comparable to the leftover of a baryon symmetry, right? So I can go on, and there's lots of speculation we can go. But one possibility is the possibility of the quark nuggets for dark matter. Basically, you can think about the energy pi. Instead, dark matter is dark, but the dark matter is made of the quark nuggets, and the ordinary matter is made of the ordinary nucleon, for example. So there is some possibility. Here, I'm kind of ignore lots of a universal story. How can make this happen, for example, right? But at least I think this is could be some kind of a motivation and to think about the possibility to explain dark matter using some possible existing states in our own QCD. So that's has a reasonable motivation in my opinion. But now let me come back to ask: do we know the how much we understand, right? So because previously we treated that calculation, degenerate Fermi, free guys, no interaction about those quarks. That's obviously is too crude. And now let us ask how much we really know about the quark nuggets property. So here, people, obviously, there are some hardcore perturbative QCD people. So they are doing like a 2-loop, 3-loop calculation to calculate the so-called pressure, which is minus of the ground potential versus the chemical potential of the baryon. And then they can make some prediction. Right? So here, which I just give you an idea, depends on the another parameter, which is X. So probably everybody know, right? So we know that the gauge coupling rounding, QCD gauge coupling rounding, you need to specify the renormalization scale. Here is a mu r. So here we just define a parameter, which is the renormalization scale divided by the baryon chemical potential. So here you can see that a slightly different renormalization scale depends on 2 flavor or 2 plus 1. Perturbative QCD calculated result for I can think about this is equation of state. When we care about the quark matter or quark nuggets, we pretty much care about perturbative QCD calculated pressure, and also this vacuum pressure, which is like because we say, oh, this is setting in the not in the global vacuum state, so therefore you need to subtract the Geiger parameter, and you want to anticipate this is a stable object, then you want the total pressure equal to 0. So that means that given the perturbative QCD calculated pressure, we want to say that different Geiger parameter will intersect with these curves, and the intersecting point will be a certain value of mu b, and also it turns out that mu b in this calculation is also just directly related to the energy per baryon for that object. So therefore, what are the calculation? You take this curve, you give say 100 GeV, sorry, 100 MeV for the Geiger parameter, 1/4 power. Then you intersect, you will get the mu b for this curve, for example, to be maybe 950, for example. Right? So that is the way we can read. From that reading, we can get the so-called stability of the quark nuggets. So let me orient yourself. Suppose we fix the renormalization scale x. Suppose x is 2.0, for example, right? So then you can see that the blue curve, this boundary, that means that above, if the Geiger parameter is above this, like 120-ish MeV, then it's not stable, which means that quark nuggets energy per baryon is higher than 930 MeV. Otherwise, it's stable. And similarly for 2 flavor, then we use this dashed line, which is even lower. So this tells just naive. Say if the x is a little bit or slightly above a certain value, 1.5 readmission scale. We trust our predictive QCD calculation. If the bag parameter is below 120 or below 100-ish, then we can potentially have a stable prognosis. It turns out that this kind of question can be answered, and if we know the bag parameter, if we can fix the readmission scale. Okay, how much we know the bag parameter? So the bag parameter is non-perturbative, and because the bag parameter is the, in some sense, is a QCD vacuum energy. To get that information, we need a non-perturbative tool. So as you probably everyone knows, the lattice QCD probably is a little bit unique non-perturbative tool to provide some information about QCD, right? However, the lattice QCD cannot directly simulate a baryon dense material because there is some sign problem, and you cannot use that to define well-defined statistics. However, recently it turns out that people also, lattice QCD people, they can also study another so-called isospin dense matter. So, for instance, you don't immediately care how you realize that matter, but as a theoretical framework, you can study isospin, which is the chemical potential for down quark is opposite of the up quark, for example. Then you can write down what is the partition function, and you have the Dirac operator, and with the chemical potential, because the up quark and the down quark is has opposite chemical potential. It turns out that the product of those two fermion determinant will be complex conjugated to each other. So therefore, this will be positive definite. So therefore, the lattice QCD potentially can simulate this. And the simulate this, then potentially can also give us some ways to contain some kind of non-perturbative information. Okay, so I just give you the idea. And what we did is trying to take the lattice simulation based on this isospin dense material. And so they calculated the pressure as a function of the mu. Mu is what the specific isospin mu, right? So previously defined. So they get some data point, which is the blue band. There's some error, so that's not super important. And we can take that perturbative QCD calculated result and minus the bag parameter, for example, and to do the fit to the lattice QCD data, and then we can get some information about what will be the bag parameter. For instance, what is the non-perturbative information contained in the lattice QCD simulation. It turns out that the central value from their data is preferred to be 0. And here I just demonstrate, suppose the bag parameter is large, for example, 250 MeV, and you can see that you will have sizable deviation from their data, trying to share the feeling that the lattice QCD is sensitive to the bag parameter to a certain level. But obviously, we can also do a little bit more careful data analysis, quantify the error bar, and so on, right? So, and by doing that, then we can also get a more useful information. But before I talk about that, there are also another lower bound for the bag parameter, which is a little bit easier to be understood. And so if we write down the QCD Lagrangian, we can write down the trace of the so-called trace anomaly. The trace anomaly will be beta over 2G, and also the MQ 1 plus gamma M. Gamma M is the anomalous dimension of the mass parameter in for the quark field. Again, there is lots of uncertainty, a lot of unknown. So in essence, we don't know what is the vacuum energy for the QCD. We don't know the gluon part. Sometimes we don't know what is the expression value of this. If someone can tell me, that would be great. And but there is some minimal information we know. We know the quark part. We know MQ times Q bar Q. Why? Because we have this famous like a GMO R relation we kind of learned in the introduction of particle physics. So which is suppose we define this BM, and which is a summation of a vacuum expression value for MQ, Q bar Q. So this by itself is a renovation scale independent, and this should be related to F pi square, M pi square, for example, for the lighter flavor. We kind of know, right? So we know the ion decay constant, we know the pion mass, we can infer what is this part for the contribution. For the strange quark, there is still a little bit of uncertainty about the lattice calculation for the vacuum expression value versus sum rule, but it's not hugely important. And as well, I will show you in the next slide. So roughly speak, you can see that it depends on the object you have. If you think about it, the object you have is let's say 2+1 flavor, like what Wheaton mentioned, like a strange quark nugget, for example. Then there is a minimum for the back parameter, which is coming from this summation of mu, uds, and q bar q, and which is should be above like 140 or 150 MeV. But if you only have two flavor, then you don't need to count the strange quark part. Keep in mind, everybody, probably you forgot. So strange quark is a factor of 30 heavier than up quark and down quark. Okay, just let you know. So the finite mass of the strange quark is what's going on here to make the MS strange quark S bar S to be larger than the up quark and down quark. Okay, so but if you only have two flavor quark nuggets, then the minimum of the bag parameter is 77. And so that this information, so that means the lower bound for the bag parameter is robust, even though we don't know what is the gluon condensation at this moment. But if we take that and we can have the left panel and the right panel. So the left panel is a 2+1 flavor, which is which roughly speaking is trying to address the Wheaton's paper about the strange quark nuggets. You can see that there is a lower bound for the microparameter, does matter the sum rule or lattice, and you kind of that's a microparameter is above the stability, which is a blue line. So which it says that given our analysis, given this interplay, we can more or less make a conclusion the 2+1 flavor quark nuggets is not stable, and from our recent analysis. On the right panel, if you only have a two flavor, because of that minimal lower bound for the microparameter from the GMO-R relation, is still can keep some open parameter space. The lattice analysis, data analysis, I was mentioning about that isospin dense material, and can give an upper bound for the bag parameter above 150 MeV, which is not yet give us a robust answer. In the future, if those lattice people, they can do more simulation, in principle, they can address this question. So I anticipate that this question, the stability of the quark nuggets, could be answered in the near future, in the next few years. And we will know that in our QCD, or even in the periodic table, do we have some other exotic nuclei, and do we have another type of state? So this, in my opinion, probably independent of dark matter. I found this to know the answer for this question is super interesting and also important. Okay, so that is for the quark nuggets in our QCD. But obviously, if we don't care about our QCD, we care about the dark QCD, then there are lots of more freedom you can anticipate. So which probably I don't want to dwell on that much, right? So in principle, you can just change the number of color for the dark QCD, which is ND, the number of flavor, which is NF. Yeah, if you have some dark QCD with a sufficient large number of quarks, dark quarks, for example, you potentially can get a more stable, right, for the quark nuggets compared to the free dark barrier. But obviously, in my opinion, that's less economical if our own QCD can explain something, especially if you eventually can address the dark matter question. Okay, after said that, then let me in the last part and trying to give you a little bit of idea about formation. Just give you a test. Objects. Okay. Probably the example. So you can first think about the question is how about an ordinary nuclei, right? So ordinary nuclei. So first of all, we have the light elements from nuclear synthesis, BBN, right? So we have a helium, a deuterium, and the lithium, and so on, right? So we have a successful BBN and up to a little bit anomaly about lithium-7 problem. But for heavy element, for ordinary nuclei, heavy element, I think in my opinion, in the last few years, especially after this event, gravitational wave, 2017, so which is this neutron star binary, neutron star merger events, it nicely demonstrated the following statement. If you look at the earlier paper, like 1989, by those gentlemen, so which is they want to say that the neutron star, they anticipate or they predict the neutron star merger potentially can explain the heavy elements through the so-called R process, which is a rapid neutron capture process, and as that use that to as a way to explain the heavy elements in our galaxy and in our Milky Way galaxy. And so on the right side, which is some people did do some data analysis for a certain element, which is the thallium, and which is I think next to the iodine. Iodine is a little bit important for human being, right? And so they then demonstrated that some spectral line of this specific TE element as a function of time after the merger, neutron star merger, and which kind of can be explained very well, and about the amplitude of the spectral line, for example. So give us kind of direct evidence that the neutron star merger is generated some heavy elements. Okay. So after says that, if I'm thinking, if we want to think about some quark nuggets, we can also think about two little bit flow chart, right? And when I think about it, is it before BBM or not, right? So if it's after BBM, which is no, so you can think about maybe also physical object, like a neutron star merger, since they can generate heavy elements. If you think about your quark nuggets can exist, maybe they can also generate quark nuggets, for example. Right? Or if it's not, so if it's before BBM, so then you maybe can depends on what's your initial condition, whether you initially have the baryon asymmetry or not. So if you do have initially have a baryon asymmetry, then maybe there's some phase transition way you can generate the quark nuggets from the early universe. Or you maybe you don't have even have a baryon symmetry at the beginning. Maybe the moment you generate the quark nuggets, you're also trying to explain the baryon anti-baryon symmetry, for example. Then you maybe have the baryon symmetric universe. So that's probably a little bit more challenging to study. And in my opinion, this has not been studied that well. And okay, so let me just talk about give you a test from the phase transition, first order phase transition, which is literally what has been worked out in 1984 paper by Witten. So what is the kind of a cartoon picture? So you can think about it, there is a phase transition temperature of the QCD, if QCD is the first order, okay, question mark. So around that phase transition temperature, maybe is 150 MeV, and then you have a bunch of quarks, gluon. So I use a red color to denote this is a high temperature phase. And later on, then you have the bubble, low temperature bubble, and they pop out like cooling, like we are boiling water, right? So those bubble popped out. Those bubbles that they are low energy phase or confinement chiral breaking, and they will meet. They expand. They will meet quarks. Those quarks, if they get inside, they should become hydron, right, or baryon. Then they will decide whether they prefer to stay outside to be like a quarks, or they want to stay inside to become baryon, right? So it depends on the relation, and maybe if they prefer to stay outside, that means that those quarks, they meet the wall of the bubble, they will be bounced back, and that means that the bubble is pushing those quarks, and as it expands. At some point, you expand. Maybe there's still a little bit baryons stick inside, but most of the baryons maybe stay outside, right? At some point, you maybe have the low energy phase occupy 1/2 of the volume. You can think about the most part of the universe become the low temperature phase, which is kind of close to be finishing the phase transition. Then you can have the high energy, high temperature phase to be small region. And then you can think about that will be the site to have the to form the quark nuggets. So so then gradually they will shrink, and then they can form the quark nuggets, and outside you have an ordinary neutron and proton, for example. So this will be one possible way to form. If you use this one possible way to form, you can estimate what will be the generic quark nugget mass, and based on this simple order of magnitude estimation, you will get the mass to be like a 10 to 14 gram, and the radius is tiny, is 1 centimeter, and so it's tiny, but very heavy. This mass is matched to the beta cross mass. And another way you can think about, if you think about this, is like a micro neutron star, and because the neutron star usually is like 10 kilometer, so this is like in terms of the radius will be like a micro neutron star, for example. Just but there is lots of uncertainties about this estimation, so you should take this as a grain of salt for the actual prediction. And also, there could be later evolution. There is additional complication can happen in general. But you probably already know, right? Our QCD is not a first order phase transition in the high temperature to low temperature, is a crossover. And so that means that even we want to speculate to use quark nuggets as a dark matter candidate, we still need to add some new physics beyond the standard model. For example, we can, so here in the last year, I think we were saying that if you have some domain wall, if those domain wall collapses due to the QCD, and that potentially can change the QCD phase transition, potentially can provide some QCD first order phase transition for QCD, for example. So what is showing here is the phase transition temperature versus the theta angle in QCD, and even theta angle equals to pi, there is a possibility that the QCD phase transition is the first order, but therefore you need to have some domain of the L inverse to be theta equal to pi. Some other domain is theta equal to 0 after QCD phase transition, and eventually the theta equal to pi domain will try to disappear, become theta equal to 0. So there is some little story if you're interested in read those papers. Okay. But obviously that's for our QCD. If you talk about for dark QCD, it's a little bit easier. So there is a much wider range of possibilities. You can have a first order phase transition. But again, I also want to downgrade a little bit the chance to have dark QCD because you want to introduce a brand new sector. And, so it's less economical compared to speculate that our standard model QCD can provide some interesting dark matter candidate. Okay. So yeah, if you dark QCD, there are some various of the mass depends on the phase transition temperature, and generically, if your dark QCD scale is high, you get the dark quark nuggets to be lighter. So there is a little bit of inverse relation here, and 2 - 3 par, based on some simple estimation one can have. So those things is if you're curious about what will be the typical prediction for this kind of dark quark nuggets mass versus the dark QCD scale, and so this will be some benchmark formula to be used. Okay, so after I said that, probably last 5 minutes, I just give you a little bit of test about how do we detect those microscopic dark matter. So short answer is there are lots of fun to think about how to detect those microscopic dark matter, because that's not the ordinary dark matter direct detection. Okay, so what does that mean? So if you think about dark matter direct detection, if usually we have the particle and there's some detector, right? And then you care about the flux, and you can calculate what is the anticipated interaction rate. So that will be related to the lumbar density, which is the rho over dark matter mass times the velocity of dark matter times your detector area times the experimental running time. So here, just give you some number. If my dark matter is not 1 GeV, if it's 1 gram, keep in mind 1 gram is 10 to 24 GeV. And if the detector is 100 meter, that's already a little bit sizable, right? And, then you anticipate like 10 years, you maybe get 1 event. So basically it says that if the dark matter is like above gram, you don't need to think about using ordinary detector direct detection experiment to search for those objects, right? So then what kind of detector you should think about, right? So earlier time, people talk about like a mica, which is some ancient mineral, and because those ancient mineral they exist for super long time, and the microscopic dark matter like quark nuggets maybe can penetrate the mica and leave a little track. So you are trying to detect some tracks in some mica. Or there are some neutron star can easily capture those quark nuggets, and after capture, the quark nuggets maybe can convert the ordinary neutron star into quark star, for example, and so that will change some generic property of the neutron star, and then you maybe also can use that to set some constraints about what's the flux. So what you're showing here in this red curve, that is the assumed object is follow the dark matter energy density. That is the flux. You can see that there is possibly some intermediate range of the barrier number is excluded, and but above like 10 to 31, it's still allowed. In the lower end, it's still allowed. But if you talk about like a barrier number very few, like order 100, then there's some other searches like AMS and so on to search for the quark nuggets, for example. But it's probably less relevant for dark matter. So this is one possibility, right? And maybe you can also go to larger detector. For example, at this time located at Madison, we have a huge collaboration, which is called IceCube. IceCube is much bigger kilometer size detector. And we did some analysis. We found that using IceCube, potentially we can get a mass which is 10 to 24 GeV, which is 1 gram. So which means barely touch 1 gram mass. And but there's still lots of possible parameter regime, which is not easily covered by the current one. And here, I think I also want to show you another idea, which we kind of relate to the yesterday's lecture about the magnetic black hole, right? Magnetic monopole. And just to share the idea. So we can also analyze, for example, the Earth's magnetic field, for example. If you think about it, there is monopole inside of the Earth's magnetic field. So then you maybe can think about use Gauss law of the Earth's magnetic field to know that whether there is a monopole component in the Earth's magnetic field. So it's kind of interesting. Like this is like translation of the paper by Gauss in 1838, and then Gauss also mentioned that the possible. So basically, he's trying to analyzing the Earth's magnetic field data at that time. And he also pointed out that, maybe one should also check the magnetic monopole. And so with my collaborators, we kind of analyzed that, and we didn't find any magnetic monopole, but we found that the data about some satellite measurement of the magnetic field is consistent with dipole or higher moment. So, but we can say a little bit how much magnetic charge of the inside of the Earth can be. So, which is not super important, but it's kind of fun to share the idea if we want to search for all kind of way. So about the quark nuggets and like what I was emphasizing, right? So I kind of a little bit amazed by the neutron star merger events because there is some speculation that the inside of the neutron star could contain the quark matter core. So that means that when you have two neutron stars merge, the core material maybe can eject out. That potentially can be the quark nuggets. Then the question is, how do we know that busy environment is producing the quark nuggets? In general, maybe we can study some property of the electromagnetic property of the quark nuggets, for example, or maybe we can also study some like a quark nugget atoms and calculate some spectral line of atomic transition lines, for example. So yeah, so here I don't want to give you any concrete number, and just to share, when we think about the microscopic dark matter, there are lots of other more bigger wide range of possibilities one can have here. So let me stop here. Thank you. So I cannot hear you guys. Probably muted.
Thank you very much for Professor Bai's very interesting talk. Any questions?
Thanks for the great lecture. May I ask what would be the cosmology for the Q balls? Is they able to produce the relic abundance, and what is the how to create so much charges for those Q balls to be documented?
Let me think. Yeah. So it's a little bit similar to the quark nugget case, in my opinion. Yeah, if we look at the Lagrangian here, if we just take this Lagrangian, the phi particle can also generate a Coleman Weinberg potential for the Higgs potential. It turns out that if this coupling is large enough, let's say order 1 or order 3, you could have electroweak symmetry phase transition to be first order. So therefore, if you have so it's a similar, so you have the first order phase transition, this time is electroweak. If you do have then depends on whether you have a quote unquote a symmetrical number for phi. If you have a let symmetrical number for phi, then it's a similar story like Wheaton's first order phase transition ways to form the charge. So you can estimate what is the total charge of phi charge in one Hubble patch. Then you can say how many nucleation sites when you have the first order phase transition. Then you can split that total charge into individual site charge. And you can use that to estimate what is the charge will be. And I think it's also probably similar to UNI, it's electroweak, but that dark quark nugget one has a little bit more broader, broader plot. Let me show you give you some idea. If so if we have the red panel, if we want to use electroweak, so this star point is a QCD scale, which is 100 MeV. But if we go to the electroweak, will be here, and then you anticipate generically based on this estimation, and you will get like a 10 to 3, 10 to 4 gram for that electroweak symmetric Q-ball object. Right? Keep in mind there is some uncertainty about the detailed first order phase transition property that will can vary a lot, and so that's why there's a little bit of wide range of prediction provided here. Good question. Thank you.
Yeah, thank you. But can it produce the relic abundance?
Yes. So the relic abundance for those cases, it's kind of so here it's almost like a put by, not I want to say put by hand. It's you already have the asymmetrical number. So if you think about the ordinary baryon, right? So the asymmetrical number, let's say you have 10 to minus 9, and then you have the proton mass, and that determines the ordinary matter energy density. So here it's a similar thing. You say that I have the object energy per charge, let's say 100 GeV, right? So therefore, you just need to have less asymmetrical number. So you say I don't need a 10 to minus 9. I need a like 10 to minus 10 asymmetrical number for this biparticle. Then they will provide the abundance to be the dark matter allowed one, right? So then you can trying to say, oh, then how do I explain the 10 to minus 9 for the ordinary baryon antibaryon symmetry versus 10 to minus 10 dark or phi particle or dark matter anti-dark matter symmetry, right? but because they are kind of comparable, so there could be some little bit common origin. So this kind of belong to the similar class of asymmetric dark matter model. So that's the way to accommodate the abundance.
I see. Thank you.
Hi, I have a question that in QCD phase diagram, when the phase transition you are talking about is the chiral symmetry restore or breaking. But if you go to higher density, there could be like quark pair appearing and color superconductivity phase. So does it come into the quark nugget?
We did take that into consideration in this analysis. Turns out that for the isospin, even for the previous plot, for example, this calculation, there is also the color superconductivity, also color flavor locking phase. For the isospin dense material, the so-called gap parameter is large, and that has been taken into consideration when we fit the lattice data. For the baryon dense region, it turns out that that gap parameter is small and is still negligible to change the total energy per baryon of the quark nuggets. So it's a little bit less important. But indeed, we did discuss those issues in the paper. You can take a look.
Thanks.
Thanks for the very interesting report. I have I'm a little confused about. It seems that you assume the confined vacuum, the force between the confined vacuum and the quark, is repulsive. Since we know in quantum field theory we know the force between the two quark are repulsive, but here it seems that there is a scattering between the confined vacuum and the quark. I think it's a little different. So I don't know why you assume the confined vacuum, the force between the confined vacuum and the quark is repulsive.
So here basically, suppose you don't have quarks, right? So like a vacuum state, right? So the vacuum state, you say outside is a QCD vacuum state, because the vacuum state, that's lower energy state, and so that means that those lower energy state is preferred. So that means that if there is no quarks, then you will have those this red region or pink region to be occupied by the ordinary vacuum state of the QCD, right? Because they want to go to the lower one. But however, because you have quarks inside, then there is quarks because they are fermion. You cannot squeeze them too much because at some point you realize that those quarks, two quarks cannot occupy the same state, right? Because they cannot. Then there is a degenerate Fermi pressure to kind of hold them, and that is repulsive for when I talk about here. I just want to say that if you think about a neutron star or white dwarf, it's a similar situation. You have a gravitational pressure wants to hold, push those electron for the white dwarf case. And occupy the same state, right? So that generated a Fermi pressure to counterplay the gravitational pressure. Here is the degenerate Fermi pressure counterplay the vacuum pressure.
Okay, let's say I mean when you say the formation of the quark nuggets can come from the first order phase transition, right? So at that time maybe the fermion maybe the degenerate fermion pressure is not that large. So
That's
why
correct.
why can't a quark just go inside the confined vacuum and
Yes.
hadronization?
Hadronization, yeah, very, very good. So for that case, very, very good. So that's a little bit probably too detailed question, but it's a relation between, let me get into that cartoon picture. It's a relation between the phase transition temperature versus the baryon mass. Let me use those three quark, right, for example, right? So at this QCD phase transition, the temperature is around let's say 150 MeV, right? 3 quarks, that's maybe like a 500 MeV, right? But if they want to get inside, then they want to become like a baryon, and there is a minimal mass for the baryon, right, which is 930-ish, 40-ish MeV, right? So that costs energy, right? So that means that only some kind of a little bit energetic quarks, 3 quarks, for example,
yeah,
they have enough energy, they maybe can penetrate the wall to get inside. And otherwise they will be reflected back. But how much of that is depends on this kind of a relation between energy of those quarks versus the proton energy, proton mass inside, right? So that's a little bit more dynamical question. But in generally, you could anticipate that they have a little bit of preference for the quarks to stay outside and rather than inside, right? Because of the hierarchy between the proton mass versus the phase transition temperature, right, at this moment. Yeah.
Okay, but here since the bubble is expanding and it put forward the quark and
Right.
and maybe it can accelerate the quark.
Correct.
So
yeah, one should take that into consideration. One should take into the gamma factor of the wall, right? So into consideration to calculate properly what will be the rate for those quarks, what we call like a reflection coefficient, right? For example. Yeah.
Okay, thank you.
Okay, I think we have enough questions for Professor Bai. Let's thank him for 2 great lectures.
Thank you, everybody.
Yeah, thank you very much. Thank you.
Enjoy the school. Bye.
Thank you. So let's take the lunch break, and the lecture in the afternoon will start at 2 p.m.